Buddy, how are we doing today? Oh my goodness. Welcome everybody to the stream. How many people do we have in here? I don't have any way of checking this. I just realized. Oh my goodness. Hold on just a second. Let's see. How many people are in here right now? This is already off to a great start. Hello everybody. How are we doing today? It's the night before your guys' exam. Sorry, I'm going to my live. Let's see, how many people do we have in here? 205 people. That's actually more than AP US History. My goodness. All right. Well, I didn't expect anybody to show up to this stream. I'm going to be real with you. I expected everybody to show up to my AP US History stream because that kind of went a little viral at the end there. But here we are for AP Calculus, everybody. How many people are in this chat that were here last year for the AP Pre-Calculus exam? How many people are my last year OGs? How many people we got? I want to see this here. Sorry, my stream is really delayed, so it's going to take me a second for the chat to catch up here. Me. Oh, here we go. Here we go. Here we go. Oh, my goodness. Oh, there's some people in here. This is great. All right, this is what I wanted to see. All right, everybody. So really quickly, I know we have some people in the chat saying to begin. I just got to go over a few disclaimers. So there's about 200 people in here right now. It is only going to keep growing as the stream goes on. It'll probably level out in the middle, kind of like a logistic function if you're in Calculus BC. But yeah, so it's going to keep growing. That means that there's going to be like 400, 500 of you in this chat. I'm not going to be able to necessarily appease everybody. Like I'm going to try and we're going to go over, a lot of you asking the structure of what will happen. We're going to go over units 7 and 8 because those are the units I wasn't able to upload at the end of this year. Once again, apologies for that. I wasn't able to upload videos for them. So we're going to go over briefly what units 7 and 8 entail. We're going to go over some practice questions for those. And then we are going to go over an A-B practice exam. And by practice exam, I mean I scoured the internet. I found a bunch of different practice exams that you guys likely don't have access to or just probably didn't find. And so we are going to go over those questions together on stream. And like I said before, I won't be able to appease everybody. I already have very good videos up on this channel. I'm a video editor over anything else. I'm not a live streamer. So if anytime this stream seems stale or not worth it to you, you're not obligated to stay here at all. Feel free to watch my videos. Feel free to go watch the Algebras videos. They're very good. Okay. So this is not a pre-recorded stream for anybody who's asking. I'm currently live. In fact, my time management is horrible. My dinner is over there, and I didn't have time to eat it because I had to start this stream. So definitely not pre-recorded. Anyway, so without further ado, I think let's start the stream the best way I can, and that is saying welcome to Unit 7 and 8, guys. So, yeah, once again, for those who are asking, sorry if this is a BC stream. This is an AB stream, meaning most of the content is going to be all AB. There's going to be no BC only topics, but most of the BC exam is AB, so take that for what you will. But anyway, welcome to Unit 7 and 8. So your idea here is that we've introduced derivatives, and we've gone through them ad nauseum, and we've introduced integrals now for Unit 6, and we are going to... Unit 7 is a very easy unit, so there's not going to be too many questions on it. Honestly, this entire slideshow is not that long. But anyway, let's get started on this. So, Unit 7 and 8. Unit 7 is titled Differential Equations. Now, the idea with differential equations is, well, anyway, let me grab this. So, the idea with differential equations is you have dy dx, and it is just going to be equal to something. Now, it doesn't really matter what it's equal to. It's just going to be equal to something. And you're often going to have to solve for the original function, which is just going to like be f or something, f of x, whatever. It doesn't matter. So, oh my goodness. Sorry, I'm using... What is going on? Okay, I'm using Canva today. We're going to use PDF later. So, let's start off. So a lot of problems you're going to receive in Calculus AB Unit 7 is going to be specifically word problems. So if you see anything that ever says it is directly proportional or just proportional, directly proportional or proportional, so if A is proportional to B, that means A is equal to a constant K times B. If something is inversely proportional, or another way to say this is proportional to the reciprocal. If something is proportional to the reciprocal or inversely proportional, so if A is inversely proportional to B, that would equal A is equal to a constant K divided by B. So just look at that in your differential equations. That's kind of the start of everything. Now we are going to go over an example. If I have my slide clicker, which I'm starting to realize this is going to be a fun stream if I don't know how to do this. All right, so a curve has a slope of dy dx equals 6x minus 4 over x at each point xy on the curve. What is an equation for this curve if it passes through the point 1, 3? Okay, so we start off with a differential equation. We are asking what dy dx is obviously the derivative. So we're asking what is an original equation, so f, I guess, or it doesn't tell us if it's f. We'll just call it f, whatever. So we're asking what the original function is if it passes through this point 1, 3. So let's first simplify this down. So we have 6x minus 4. Minus 4 all over x. Oh my goodness. My handwriting hopefully gets better throughout the stream. So let's simplify this down. So 6x minus 4 over x. Since they're both over x, this is the same thing as writing 6x over x minus 4 over x, because they're, as you can see, they're both in the numerator and there's both in the denominator. And then this would be equal to, since the x's cancel on the 6 here, it would be equal to 6 minus 4 over x. Lovely. Okay, so now that we have this simplified down, to get to our original function, we need to take the integral. So we put this all and take the integral of it. So the integral of 7 minus 4x with respect to x, of course, then that would equal, what would that be? 6x, or sorry, just 6x to the power of 1. So 6x minus 4, the natural log, because it's on 4 over x, the natural log of x. And then this would be plus c. So this is what the original function is equal to. But remember, we were given a point earlier. We were given a point. Oh, wait, sorry. Yeah, no, we're good. So we were given a point earlier, 3, 1. So we already have x. This would be y equals. We already have x in this original function, and we have y on the outside. So 1, 3, x, y. Let's plug in the different points. So 3 is going to be our y. So 3 is equal to 6 times 1 minus 4 natural log of the absolute value of, 1 plus c. So let's simplify this down. So we get 3 is equal to 6 minus, the natural log of 1 is just equal to 0. So 0 times 4 is just 0, so we can just say minus nothing. So we'll just do plus c. Then 3 equals 6. So we subtract 6 from both sides, and we get c is equal to negative 3. Lovely. Okay, so that means it's asking us, the question is asking us for an equation here. So an equation that best, oh my goodness. Let's delete that. An equation that it's, oh my goodness. I'm already such a great live streamer. Okay, so an equation is going to be this original line right here, just with the c that we just figured out plugged in. So we get y is equal to 6x minus 4 natural log of the absolute value of x plus the c we found earlier, so negative 3, so it could have been minus 3. So this could be minus 3 or plus negative 3, whichever one you want. And this one right here is going to be our final answer. So this is the idea for differential equations. Okay, next one we are going to do is going to be this one right here. So the difference between this one and the last one is that this one has a y as well in the equation. It has a y. And so when we have a y, we have to do something called the separation of variables. And the idea here is that we want to get this dy dx here. This is not a fraction. This is just saying the derivative of y with respect to x. Now, this technically is not a fraction, but for differential equations, we can actually treat it as a fraction. So the idea is we want to get the dy and y on one side and the 6x and the dx on the other side. So let's start off by doing I guess we can just multiply, get the y on this side. So we can get dy dx. And if we divide both sides by y, it would just be 1 over y, like that. And then this would be equal to, we got the y off that side, so that's 6x. Lovely. Okay. Then we want to get the dx off of this side, so dx will multiply it over here. So we get 1 over y dy equals 6x dx. Now notice, these are, because we have the y's and x's on both sides, now we can integrate. But this time we actually integrate both sides. So we integrate this side and we integrate this side. Okay, we're going to bring the integral up here. Lovely. Okay, so the integral of 1 over y dy, that would just equal the, sorry, I'm using a cheat here, the natural log of y, because it's 1 over y. And then this would be equal to, because we have to do both sides, so this would be equal to, let's see here, we have 6x, so we have 3, or wait, no, it would be, sorry guys. Sorry, my intuition's not great today. Oh my goodness. So we have 6x, so we do 6x to the second over 2. So 6 over 2 is equal to 3. So we'd get 3x to the second. And then, of course, that's all going to... So this side technically would be a plus c. Like this is going to have a plus c because it's an indefinite integral. But the thing is, when you're doing this differential equations, you don't have to have multiple plus c's. Like this would be plus one constant. This would be plus another constant. So we can just combine them together and say plus a constant at the end. Just like that. Okay. So now we have 3x squared plus c and the natural log of y. So what we're going to do here is try and simplify this out. Now, if you remember, the way to simplify a natural log is to have e under it. So we do e raised to this. But what we do to one side, we have to do to the other. So e raised to this. So now we get the natural log of y, or the absolute value, I should say, of y is equal to e to 3x squared, squared plus c. So the natural log of y here, or sorry, the absolute value of y. We'll get to that in a second. But let's talk about e here. Because this is technically, if we're looking at this term, we can use the, I believe it's the product rule of exponents. We can use, because 3 plus c is equal to e to the c here, because we have the c. I'm just doing the c first just to make it easier, times e to the 3x squared. Now this right here, this term is equal to this right here. This is equal to this. But we still have this absolute value. So what do we do? Well, if you remember, this is more of an algebra trick. The way to get rid of an absolute value is to do plus or minus on both sides. So we do plus or minus on this side. That gets rid of the absolute value. But that means we have to do plus or minus on this side. So plus or minus e to the c times e to the 3x squared. Beautiful. Now, this is a little bit... This is something called a little bit complex. The idea here is that e to the c, like imagine if c is 2, e to the 2, that is just equal to a constant. Now you might be saying, well, plus or minus, that means there's going to be a plus or minus answer. But no, what we can actually do, e to the c is just going to be a constant, so we can absorb the plus or minus into this constant. So we get y is equal to, we'll just say this is another constant, not the same c we had here, or the same c we had here. It's just going to be a different constant c, so we can call it a, we can call it any other letter, but we'll just call it c again. This is just know this is a different c than the one we had up here. It's going to be c times e to the 3x squared. Beautiful. And that right there is actually our fully simplified answer. So this is your idea with separation of variables with differential equations. Okay, let's keep going, everybody. Exponential differential equations. Now, these are a little bit different. And I should say, I forgot to put the derivative here. So the idea here is that the exponential differential equation is going to be dy over dt equals ky. Now, the way we do this, of course, is equal. We take this one, which is the parent exponential function. You know, a is the base, or B is the base, I should say. A is the growth factor times to the t. This is just the same thing as ab to the x. That's the parent exponential function. So the way we get to this dy dt is by doing separation of variables once again, and we get to this. Now, I don't want to do the separation of variables because I already know that every exponential function is going to be modeled by this constant k times y. So let's go through an example here. A bacteria colony starts with 500 bacteria and grows at a rate proportional to its current population. After 3 hours, there are 2,000 bacteria. Find the population as a function of time. So we have population, so instead of x as our variable, we'll just say p for population. We're given a few things here, but like I said, every exponential function is going to be modeled by the same thing. So we are going to write dp dt, because it's with respect to time here, is equal to ky. Because remember, that is the same exponential, or sorry, not ky, it would be kp here. Kp. Beautiful. Because remember, every exponential function is modeled by the same thing. So now, before we plug anything in, we have to do the separation of variables and integrate this once again. So we get the k, we get the 1 over p on this side. So we get, this would be equal to, 1 over p times dp dt, which would be equal to, I should say this is an arrow, which would be equal to just k. But now we got to get the k on the other side. Wait, am I messing this up? No, we're gonna get the derivative of time on over here. So we get 1 over p dp is equal to k dt. Lovely. All right. So now we integrate both sides. Once again, integrate both sides because it's separation of variables. So we get the natural log of p, absolute value sign, or don't forget it, is equal to, what would it just be k? Yeah, because we can't really integrate that, so it would just be kt plus c. Beautiful. All right, so now this is our integral. Now I want you to notice something. Sorry, I am losing my mind over here. So yes, this would be equal to p. So the idea is if you're ever integrating a exponential function, it would always be equal to something called kect. It is an annoying thing to say, but p is equal to c e to the kt. Look at this. So, with this idea here of plus c, we can start plugging in the PE is equal to the CEKT. Sorry, I'm trying to understand this too. I'm struggling for some reason to get this. So we already know that C, the population, is equal to 500. So C is equal to 500. So let us plug this in to the function P is equal to CE to the KT. Sorry. So PE is equal to the CE to the KT. It's kect. Okay, this is going good. P of T is equal to 500 E to the KT. Sorry, I can't believe I'm doing this. Okay, something's going wrong here, guys. Everybody. I want to come back to this in a second. I'm sorry. My live stream brain is fried right now. I'm going to come back to this in a second. I apologize, everybody, for doing this wrong. But something has gone wrong here, and I can't make up my notes here at all for some reason. So we're going to come back to this in a second. Once again, I apologize, guys, for this one. I will take the blame on it, but something has gone wrong here. Thank you guys so much. I apologize once again. Let's just talk about something different. We'll come back to it later. Not a live streamer, by the way. So this is the next one, slope fields. Sorry, I just don't want to be dragged on by one when I clearly don't know how to do it. I'm just going to be real with you. It's pretty difficult. Okay, so why this is a slope field. Now the idea of slope fields is you're trying to take the derivative. You're trying to take the derivative function essentially. Or sorry, you already have the derivative function right here. I'm sure you've never seen somebody skip a question, but we're going to move on. So your idea with the slope field is it gives you the derivative or kind of the slope at each singular point. So if we had a point like right here, it would probably, you can kind of see, you can follow the ways of the graph here. Sorry, that's not a straight line at all. It'd be something like that. Or if you had a point right here, it would be something like this. Or it didn't even go through the point. It'd be something like that. So your idea with the slope field here is that you are trying to find this is the original function's instantaneous rate of change at different points are. And so like, if we see a perfectly vertical line, we know our slope is equal to 0, but of course we don't see any perfect vertical lines here. But you can kind of see like we don't really have anything here. So we kind of come to the middle. So like if we had a point at 0, 0, we can kind of follow the pattern of the graph. It'd probably just go out like this or go out like this. That is the idea with the slope fields. And we will have a question on our practice exam later that will go over this. Sorry, I've just been totally derailed from earlier. So we will go over more with slope fields later, but this is just kind of the general idea of it. Let's move on. This is Unit 8. So once again, we will come back to this in a second. I apologize. I don't know where I went wrong here. I'm trying to find the integral of kt dt. We didn't write the dt on that side. Okay, the dt. Yeah, sorry. We're going to go back to that later. I apologize for everybody who didn't understand that because I didn't understand it either. But we're going to go back to it later. I know what we're doing now. This is average value of a function. So basically, we just have a bunch of formulas for Unit 8. That's the idea. The idea is we have formulas for each function here. So 1 over b minus a times the integral of from a to b of f of x with respect to x. So this is the average value function, or at least I should say the formula for average value. This is Unit 8, by the way. So getting a little more complex. I'm not going to go over an example here. Just know this formula. You won't be given it on the AP exam. Integration of rate. Now this one is a little bit more important. We will go over an example of it. So the idea is the integral of rate of change is your net change. That means rate of change here is your velocity. Net change here is your displacement. Those are just examples. It's not always going to be velocity and displacement. We will go over an example here. A candle is burning down over time. The rate at which the height of the candle is decreasing is modeled by R of t is equal to 2t inches per hour, where t is the number of hours since the candle was lit. The candle was originally 20 inches tall. If a candle burns for 3 hours, how tall is the candle after 3 hours? Okay, so we are given the function R of t is equal to 2t. Lovely. So the idea here is that the decrease here is going to be equal to dh dt, dh just the height, dt, which is equal to negative 2t. Now, if you're wondering what I just did here, it means because this is a decreasing function, because it's inch per hour, number t, the candle was originally 20 inches tall, so the candle is burning, so it's losing height. So because it is decreasing, it is going to be negative instead of positive. So that's the idea here. Now, we know h of 0 in this function is going to equal, h of 0 is going to equal blah, 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 20, because we start at 20 inches tall, originally 20 inches tall. So the idea here is the height loss after 3 hours is going to be equal to the integral as 0 approaches 3 of 2t, because that's what we had earlier, dt. Now this is going to be equal to x squared, obviously. Or sorry, t squared, I should say. Let's write that down. T squared. Lovely. And then t squared. So now we have to use the fundamental theorem of calculus, because what are we given here? We are given 0 to 3. 0 to 3. So I like writing a line on the side. You can write brackets. It's up to you. 0 to 3. So we first of all, here, I'm going to change the color up a bit. I know you guys might be tired of looking at red. So we get f of b minus f of a. So we get 3 squared, because we're plugging into this function, minus 0 squared 3 squared is 3 minus 0 is 9. Or sorry, 3 squared is 9 minus 0 is going to be just 9 again. The 9 is going to be our answer. But the idea, since we started at 20, we have to subtract 9. So we do 20 as our initial height. We subtract 9, because that's how much the candle is burnt. And then we get our answer, 20 minus 9 is 11. So 11 is equal to h of 3. And this would be our final answer. Sorry. Oh, gosh. I just did something weird. So, yeah, 11 is equal to h of 3. That's our final answer here. Okay, let's keep going. Area between two curves. Now, this is more of a BC top. This is not a BC topic, sorry. This is an AB topic still. But area between two curves. The idea here is that the area is going to be equal as from the integral as a goes up to b of f of x minus g of x with respect to x. So we might wonder, what exactly is f of x and g of x? Well, f of x is going to be the function that is greater than or equal to g of x for all x and a to b. So f of x is likely going to be your greater function. Okay, so let's go through an example of this. Let j of x equal x plus 2, h of x equal x squared. Find the area of the region enclosed by j of x and h of x. Now, of course, these are pretty easy graphs. I mean, if we were to sketch them on top of one another, so let's see here. If we had our function x squared, that's just going to look like that. And then x minus 2, here, let's do this in another color. X plus 2, so we get x plus 2. So the graph's going to look like this. The idea here is that we're finding the area of this region in the middle right here, whatever is cutting off in the middle of the graph. Now, the thing is, a lot of graphs like this, you won't know which one's on top. So obviously here we know this x plus 2 is on top, but we won't always know that. So how exactly do we figure out which one is going to be f and which one is going to be g in our original standard equation that we went over earlier, this one? How do we know which one's f, which one's g? Well, f is bigger, f is the one above, so we know it's x plus 2 already. But let's pretend we don't know how to sketch the graph at all. We find our intersection points first. So to do that, we do x plus 2 is equal to x squared. So we set the functions equal to another. X plus 2 is equal to x squared. Cool. Then I'm going to move these all onto one side. So negative x squared. So we're just going to multiply the entire thing by negative. So x squared minus x minus 2 is equal to 0. Then we factor this, algebra 1, of course, x minus 2, x plus 1 equals 0. And then this, of course, means x equals 2 and x equals negative 1. Lovely. Okay. So now we are given the points negative 1 and 1. So the idea here is that we'll start at the lowest, negative 1, and then comma 2. So the idea here is if we want to find which one of these, because this is our endpoints for our interval, this is negative 1 right here, this is 2. The idea is we need to plug in some value within this interval right here. We need to plug in some value and figure out which function is bigger inside that interval. So because this is nice and easy, it goes over 0, we're going to plug in 0 because that is within inside that interval. So 0 plus 2 is 2. So 0 plus 2 is 2. And then 0 squared is just equal to 0. 2 is bigger than 0, so that means our bigger function is the j of x, x plus 2, so that is going to be the f of x in our separation of values, or not separation of values, sorry, the area between two curves. All right, lovely. So let's actually set up the area between two curves. So we do the integral. Area is equal to the integral from negative 1, we just found negative 1, to 2, we just found again, negative 1 to 2 of, we'll do a full bracket here, x plus 2, because that is our first function, and then we do minus x squared, because that is our second function, all with respect to x. Okay, so now we find the integral. Now this is going to be well, actually, I was going to say we had to use substitution. We don't, because this is not raised to the power of anything. So what we can do here is we can rewrite this integral negative 1 to 2. We can rewrite this as negative x squared. So let's move negative x squared out front again. We can just rearrange it like we did earlier. So we get x squared, or or actually, no, we don't have to rearrange it. We can do just negative x squared because we're putting it on the front, plus x plus 2. That makes it easier because it's in standard form. So when we differentiate, okay, or sorry, differentiate, integrate, I should say. All right, now let's actually find this. So we get negative 1 is equal to, oh, sorry, this is, okay, we find the integral of each of these. So negative x to the third all over 3 plus x to the second all over x plus 2x, right? Plus 2x. 2d. Okay. So that's us integrating it to x all, and this would of course be plus c at the end too. Okay. But now, because we are doing a definite integral, we have to solve it between negative 2 and 1. Let's write our line on the side. We have negative 1 and 2. Lovely. All right, I don't have any space left, do I? All right, I'm going to move me up here. Apologies, guys. Negative 1 and 2. Actually, let's just get rid of my camera so I'm not covering up anything. So negative 1 to 2. So we have to plug in f of a minus f of b. So this is going to be tedious, but let's do it. Or f of b minus f of a, I should say. So let's write this in a different color. Negative. This is going to be fun. Okay, bracket. Negative 1. Oh, we're doing negative 2, sorry. Negative 2 to the third all over 3. We're writing this down, but we're plugging in 2. Plus 2, or this is over x, sorry. You guys, I'm sure you guys caught that mistake. This is supposed to be all over 2. Oh my goodness, this tool sucks. It's supposed to be all over 2. 2 squared all over 2 plus 2 times 2. Lovely. And then we, and then we plug in minus, because the fundamental theorem of calculus, we have to do minus, and then we plug in negative 1. So we get negative 1 cubed all over 3 plus x, which is negative 1, squared all over 2 plus 2 times negative 1, which we can just say is negative 2. All right. Beautiful. Now we have to do some fun simplifying. So have some fun here. We get negative 8 over 3 plus 2 squared is 4 over 2 is 2 plus 2 times 2, which is 4. And then we do minus negative 1 cubed is negative 1, but because a negative times a negative is a positive, it would be positive 1 in the numerator all over 3. And then we do plus negative 1 squared is just 1, so it would be 1 over 2. And then we do minus 2 at the end. Beautiful. Okay. And now we can simplify these down using common denominators. So 2 over 3. Yeah, so 2 would be equal to 6 over 3. So 6 over 3, this would be equal to 12 over 3. So when we do the common denominator solving, sorry, I already did it, so I'm just going to write it down. It's going to be equal to 10 over 3 minus negative 7/6. And then if we do more common denominator solving, which is this would be 20 over 6 minus the negative 7 over 6, we would get as our final answer, sorry, I'm going to have to bring this all the way over here because we have the 20 over 6 minus the negative, so we'll just plus 7 over 6. We get equal to 27 over 6. Or, go down here, 9 over 2. We're dividing both by 3. This is our final answer, guys. 9 over 2. My goodness, that took a second. All right. Thank you, guys. I appreciate for your understanding in the stream. Oh, sorry, wrong one. I got to toggle on the camera. Okay, so this is going to be all our work to find just this one. So this is the area. 9 over 2 is going to be the area of our shaded region up here, this one right here. That's going to be the area of that shaded region. All right, let's continue. Okay, this is your idea. We're just swapping the x and y here. So like I said, this is the idea. This is the function x squared right here, this one right here, that's the function x squared. This is the function the square root of x. So if we did these functions on top of one another, we would see that the square root of x is on top. That means we can take if we were to do the area of two curves, the square root of x would be on top minus this x squared, which is the square root on bottom. Now, I want you to notice that I put two formulas here. We have one on one side. This is with respect to x, but then I have with respect to y on the other side. Now, if you're wondering how we got with respect to y, what we essentially did, because this function is nice because these two are inverses of one another, so they equal one another. But if we set x squared, y is equal to x squared, we would get the square root of y is equal to x. And again, if we did it on the other side, y is equal to the square root of x, we would get y squared is equal to x. The idea here is because the square root of y is on top now, we do the square root of y and then minus this y squared with respect to y. So if you're I want you to imagine if you're looking on the y-axis, you are now shifting your graph 90 degrees. So you aren't looking at it as the case from like 0 to 1. You're looking at it on a case of 0 to 1 on this side. So just keep that in mind when you're looking at this graph. Okay. We are going to move on to our next one. Volume of cross-sections. Now, cross-sections, everybody, these are going to be a little bit difficult. Cross-sections as a whole. The good part about it, if you're an AB student, it's not really going to be much on your exam. At most, I imagine, is going to be one question. The idea of cross-sections is more like, here, I think I have a photo next slide. Like this absolute value graph we had earlier. So let's say we go back to our absolute value graph. Now, let's say if we drew like a bunch of lines on this graph that we're going across, splitting the cross-section like this. Now, from a top view, these just look like a 2D image. Now, my brain struggles to think in 3D, but if we were to rotate this graph onto a 3D plane, it would look like this. We have semicircles that are going along the top. And so the idea is like kind of with Riemann sums, if you had an infinite amount of these, you were going to make one solid shape that goes around over. I would love to draw it, but I can't. But like one solid shape that connects all of these on the top. I imagine an infinite number of these, and then like all of this would be shaded in, and the way to find the volume would be the integral of this value 0 to 1 over here of all of these semicircles together. So that's why it's an integral. So the volume is equal to the integral of a to b of a function with of the area of a shape. So we need to know our area formulas here. And so they will actually give you a lot of the cross-section equations, they will actually give you a lot of the cross-section equations on the AP exam. What you need to know is the square cross-section is equal to s squared, because s is just a side length here. So I want you to imagine a square has an equal side length all around. So if s is one side, s is going to be the same on this side. So s times s is going to be equal to the volume in here. So that's why it's s squared. On this side, the rectangle, it's width times height. You have to know one of these. So the height will most likely be given here. And so that's why if you have a rectangle where the side lengths are not even, you have the width and then you have the height. Oh my God, that's a very bad W. So this is the integral notation for the cross sections. Now, we will have an example of this on our practice exam that we are going to be doing, so we will do that a little bit later. I want to go back to this example, but I fear that I won't be able to solve it, so we're not going to do it right now. Instead, we are going to move on to our practice exam. So everybody, hi there. How's the chat going? I'm going to answer a few questions because I have to put the actual practice exam in the chat so you guys are able to follow along. So give me just 1 second, guys. I'm going to put this actual AB practice exam in the description of this video. So give me 1 second. How are you guys all doing in chat right now? People are talking about optimization. Optimization is one of those things where you don't really actually have to worry about it too much because optimization as a whole is very It's very minimal. It's only 3 topics of Unit 5 that optimization actually covers. I'm not going to cover it in this live stream because literally you are probably not going to receive a question about it in the exam. But just know that if you have to have an optimization problem, it's just setting it up as the hardest part, and then you set the derivative equal to 0 and you solve it. AB practice exam. Sorry, I'm updating the description right now to include the practice exam we're going to go over. Lovely. All right, if you guys want to refresh your streams and then look in the description. That is the practice exam we are going over right now. So feel free to refresh your stream, and it is going to be the practice exam we are going over. So feel free to refresh your stream, guys. The area, this guy asked, is the area A of x just f of x minus g of x? That is one way to look at it. The other way is just because a of x minus g of x is specifically for squares. Sorry. Over here, specifically for squares. But it might get a little bit different for triangles and half circles. So just keep that in mind, semicircles, but they'll give you the formulas for those, so it won't be that difficult to find. But anyway, we are going to go back to my face really quick. Sorry, that went to my starting stream screen. We're going to go over a full AB practice exam now, guys. Please look in the chat. This is going to be, the washer method is also going to give you the question if you have the dis method too. Again, it's not going to be worth that much on your AP exam. So anyway, we are going to go over an AB practice exam now. I've said this a million times, but I apparently have to keep saying it. Sorry, I'm trying to get this all right over here. Give me 1 second here, guys. Oh, sorry. There we go. Okay. Welcome to your AB practice exam. For those who are wondering, this is in the description. If anybody asks where it is, they will give you the area. You have to calculate the area yourself, but they'll give you the area formula, and they'll give you all the values to calculate. Okay, so this is an AB practice exam. Again, this is in the description. If anybody asked, just tell those people that are asking that it's in the description of this video to refresh their screens. We are going to cover this in a PDF. There's no answer key because I'm going over the answers right now. So yeah, let me grab my cheat sheet again because as you can see, I've been relying on this thing heavily. But I should know most of this stuff because I've covered most of these units. But anyway, we are going to start off with the no calculator allowed section. When we do get to the calculator allowed, we will use a calculator, obviously. But right now, we're not going to. So anyway, we have the limit as x approaches 0 of 1 minus cosine squared of 2x over 2x squared. Now, if you remember from AP pre-calculus, or if you took pre-calculus, sine squared of x plus cosine squared of x is equal to 1. Sine squared of x plus cosine squared of x is equal to 1. So if we rearrange this, 1 minus cosine squared of x would be equal to sine squared of x. So we can rearrange this numerator right here. I'm not going to write the limit every time because that's tedious, but we can rearrange this numerator to be sine. Here, let's switch colors. We can change the numerator here to be sine squared of 2x, not x because it's 2x, all over what we had before, 2x squared. Beautiful. And of course, we would have the limit on this side. I'm just not going to write it because it's really tedious. Okay. So one way we can rearrange this, because we have squares on both sides, this is sine squared of 2x. We have 2x squared. We can write this and say it's equal to sine of 2x all over 2x, and then we can square the entire thing. Now, I want you to notice something here, and this is probably something a lot of you guys forgot. This is a trig limit, because remember, this is the limit as x approaches 0 of this function right here, but this is a trig limit. This is one of those very, very forgettable Unit 1 topics that we have trig limits, but if you remember, the trig limit here is the limit as x approaches 0 of sine x over x would be equal to 1. This is our trig limit. So the idea is that because we already know that this trig limit exists, and you do need to memorize this for your exam technically, because we already know this exists, we can plug it into this function. Sine of 2x over 2, well, the 2's will cancel out here, so we would just get 1. So we would say this is all equal to 1, but we still have the squared, so we have to write the squared. 1 squared, which is just equal to 1. And then we got rid of the limit because we used this identity here. Oh my god, you can't see that, sorry. Yeah, so 1 squared is equal to 1. So our answer here is D, which is 1. Look at that. That's our first one done. This is going to be fun. Yeah, so the trig limits, you'll probably, I assume they'll give you a 1 question, but yeah, this is just one of those things that you might get asked on the exam. All right, next question. Let's see. I don't want to cover anything up here. Can I put myself in the top right here? Yeah, I can. You guys can see the whole thing. Cool. So the graph of the function f is shown above. Which of the following statements is false? So the idea, the limit. Okay, this is easy. This is unit 1. So let's look at each of these. So the limit as x approaches 2. Now remember, if it's a limit, if it is just a limit as x approaches a number, for that limit to exist, you have to, the left and right limits have to exist too. They can't be the same number. So, or they have to be the same number. They can't be different numbers. So this would be equal to, if you want this limit to exist, you have to have the limit as x approaches 2 from the left, 2 from the left, be equal to the limit as x approaches 2 from the right. So just keep that in mind. I'm going to delete all this really quick. So it has to be equal to both sides limits. So we have the limit as x approaches 2 is our first option. Let's take a look. The limit as x approaches 2 from the right of the graph does exist because it's going to 2, so that would equal 2. The limit as x approaches 2 from the left is also going to equal 2. So that is why the limit as x approaches 2 does exist, because it's both approaching 2. I know you see this filled in dot here, but the graph isn't approaching that filled in dot at 1. It is approaching the open dot at 2. So since both the limits go to 2, this does exist. So this is true, so it cannot be 1. We're asking which one is false. It cannot be 1. Okay, the limit as x approaches 3 exists. So as x approaches 3 from the left, here, let's erase this graph. As x approaches 3 here from the left, we see it approaches positive 5. As x approaches 3 from the right, it is also approaching positive 5. So again, this does exist, so it's not correct. Lovely. Next one, the limit as x approaches 4 exists. Now this one, x approaches 4 from the right. We go down, x approaches 4 from the right would approach positive 4. But as x approaches 4 from the left, it would approach whatever this dot is, which is not equal to 4. It would be a little bit below 2. Now, because these are different numbers, one is 4, one is the other one, the limit cannot exist. So that means this statement here is false. It does not exist. So C is our answer. Lovely. Okay. Next one. We are given a piecewise graph. Okay. Now, for our piecewise graph here, sorry, I want to make sure you guys are able to see all of it. We are given a piecewise graph here. So I know you might also really quickly just to know, I know you might see this like question 1, question 5. The reason is because I didn't put them in any particular order. I just grabbed a bunch of questions that I thought would be good to cover in this stream. So that's what I got for you. And no, I didn't cop out and put no unit 8 or 7 questions. We have that. Okay. So let f be the function defined above, so this piecewise graph. At what values of x, if any, is f not differentiable? So what I want to look here is I want to check the values and I want to check the derivatives. Now, if we look at all of our multiple choice options here, like x equals -1, x equals 2, x equals -2, x equals -1. So our lowest number here is -2, and our highest number here is 2 as our options. God, that is a very ugly color. So -2 to 2. So this last one here, x, where x is greater than 2, this does not need to be solved because there's nothing in our intervals here are none of our answers that are greater than 2. So I don't even need to worry about this one. So I'm just going to completely cross it out. Don't even worry about that one. But I do need to check these ones because all of our answer options are going to be for those ones. So first, I want to check the left side. So we are going to plug in, like it's A, we're going to plug in A. So 2 over negative 1. Or sorry, no, we're not going to plug in A. You can see where these values shift is at negative 1 because this one ends at negative 1. Or sorry, this one ends, oh my goodness. This one ends, whoa, how did I make that bigger? This one ends at negative 1. This one starts at negative 1. So because these end at this end and start, we check what they equal in the respective respective functions. So let's just really quickly check. 2 over negative 1 would be equal to negative 2. So x, and then we do this one. So negative 1 squared minus 3. Negative 1 squared would just be 1 minus 3, which is negative 2 again. So because these equal each other, we know that, yes, this is going to be continuous. So now, because it's continuous, we have to, that's one of the rules for being differentiable. Now we need to, now the easier way to do this is to check your derivatives. So for the left derivative, let's just take the derivative of, here, let's do a different color, actually. So let's do this first one, dx of 2 over x, which would be equal to 2 over x. So I had a derivative. Sorry, we just did a bunch of integrals. It would be equal to, right, negative 2 over x squared. Okay, negative 2 over x squared. I think that's right. Yeah. Okay, and then f, if we were to plug in f prime of negative 1 into this, that would equal 2 over negative 1 to the second. Negative 1 to the second is 1. So 2 over 1, negative 1, or sorry, the negative, I guess, would be outside of the interval here because there's a negative. We forgot to bring this negative down. But so negative 1 squared, 2 over 2, or sorry, 2 over 1 is 2, but with the negative sign, it would be negative 2. That's our answer for that derivative. Now let's do our right one. So this one right here, let's do our derivative, dx of x squared minus 3 would be equal to, let's see, x squared, or x squared minus 3, it would be equal to 2x. Okay. Then we plug in f prime of negative 1, which would be equal to 2 times negative 1, which is negative 2. All right, cool. Because these are the same, we know that these are, because these are the same, we know the function is also differentiable. So let's check our options now. Specifically, we already checked this one. Let's check x equals 2. Does this color look good? Yeah, I think that's a nice looking color. All right, so let's check our x equals 2 here. Let's see, where do I want to plug in the 2? I guess we can plug it in 2 squared minus 3. Let's just plug it in up here. So x equals 2. Where does 2 fall in our intervals here? It is right here. So 2 squared minus 3, because we're plugging in 2 here. This would be equal to 4 minus 3, which is 1. Lovely. So now that is the left side. The right side here, gosh dang it. All right, we actually do have to use this. That's on me. The right side here is actually the 4 minus 2. I thought we didn't have to use it, but we do, because this is the left side, so we have to do the right side. Remember, we're checking both sides. So we do 4 times 2, because we're plugging the x equals 2, minus 3. So 4 times 2 is 8, minus 3 is equal to 5. Oh, but look at that, guys. That's unfortunate. So 1 and 5 are not equal to one another, because remember, the left has to equal the right, but because these don't equal one another, it means that x equals 2 does not exist, and therefore is not differentiable. It's not continuous. It does exist, but it's not differentiable. So because it's not differentiable, our answer actually here is going to be B. So I hope that made sense. So first we checked if the function was differentiable at -1 by checking its derivatives. The second thing we did here is plug in the left and right side, because we were going to do the same process for each of our answers, but we found out it's B. I'm sorry if that little bit wonky around. But anyway, let's continue. The table of values gives the table above gives values of the differentiable functions f and g and their derivatives at the selected values of x. If h is a function defined by h of x equals f of x, that function, then h prime of 1 is equal to blah, blah, blah. So for this one, h of x, we're going to copy down what this h of x function is equal to f of x, g of x, plus 2g of x. Okay, so we have this original function. So we need to find what h prime of 1 is. Now, the first thing I'm going to do here is I'm going to solve for what the derivative function of this is going to be. So that means h prime of x going to be equal to, now this is a trap. You want to say here, oh, well, obviously it's f prime of x, g prime of x. Easy. But that's not how this works, guys. This is two variables multiplying by one another. And when you get that, it is the product rule. So remember, the product rule, you do the derivative of the first, so f prime of x. Then you keep the second the same, g of x. Then you add. You keep the first the same, or is it? Yeah, you keep the first the same, and then you do the derivative of the second, g prime of x. That is the product rule. That's just, remember that. And then plus, then we do the derivative of this, 2 times g of x. All right. Or 2 times g prime of x. Cool. All right, so that is our derivative function. Now we need to solve this for f. Now we need to actually plug in values. Now, we're looking at when x equals 1. So let's change this to h prime of 1. So we already know what a lot of these equal on 1. Like we have f prime, we have g prime, we have g prime, and we have f and g. So we actually already know a lot of these values when it equals 1 because of the table. So we can plug in these values now. So h prime of 1 is equal to f prime of x. So f prime of x at 1 is -4. G of x at 1 is -5. Plus f of x is at 1 is 2. G prime of x at 1 is 3. And then we add 2 times g prime of x at 1, which is 3 again. Hope I plugged those all in right. I think I did. Okay, so now let's do some simplification. H prime of 1 is equal to -4 times -5, which is -20. Not -20, it's +20. Thing is 20 plus 6 plus 6. So 20 plus 6 plus 6 would be equal to 32, right? 32? Yeah. 32. And so because 32 is our answer, we have to circle it over here. 32 as our answer. All right, that one wasn't too bad. We used the product rule. All right. Sorry, I'm reading the chat right now. It's a very interesting chat you guys have. All right, so there we go. That is that one. Already 3 questions in. Not bad, guys. Not bad. All right. So the next one. If x cubed minus 2xy, here, I'm going to cut this off really quick. So if x cubed minus 2xy plus 3y squared equals 7, then dy dx equals, okay, so we're finding the derivative here, but notice that we don't just have x's in our equations, we have y's too. Y. And because we have y's, that means we have to do implicit differentiation. All right. I hope you guys remember how to do implicit differentiation because I sure don't. I'm kidding, I do. But it was a very interesting thing to teach back in Unit 3. All right, so let's write down our original function really quick. So x cubed, here, I want to use a different color. I used this one already. X cubed minus 2xy plus 3y squared equals 7. Okay, now we find the derivative. So we get 3x squared, power rule. I got this. I'm so good at this. Minus 2x times dy dx. I guess this is maybe, no, this isn't related rates. I thought it would be minus 2y because we also have to take the derivative of y here. plus 6y dy dx, and then 7 would just be 0. Okay, let's simplify this even further. So we get, because we have to, this is just us simplifying, or we did the derivative of a few terms, but we had to simplify these down a tiny bit because 3 squared, or 3x, sorry. So we have to really quickly do the derivative of it again. So we get negative 2x. Or I want to get them all satisfied to one side. So dy dx, negative 2x dy dx plus 6y dy dx is equal to negative, because we have subtract the 3x, so negative 3x squared minus 2y. Minus 2y, yep. Maybe plus 2y? Yeah, it is plus 2y. Sorry, yeah, plus 2y. Because we're adding the 2y. So all we did here, we found the derivative first, and then we just separated them so the dy dx's are on one side and everything else is on the other side. So the idea here now is that because we have dy dx on both these terms multiplying, we can factor them out. So let's use a different color here, this one. So we can do dy dx, factors out from both of these. So we get negative 2x plus 6y. Beautiful. And that is equal to, again, the negative 3x squared from earlier plus 2y. Okay, and now what we can do is divide it from both sides. So because this is multiplying by this, we can divide it from both sides. So we get dy dx is equal to negative 3x squared plus 2y all over this one, negative 2x plus 6y. But because these are both negatives, we can rearrange the numerator to instead be 3x squared plus 2y, or not plus 2y, it'd be minus. That's what I was trying to point out. Wrong one. We get 3x squared minus 2y, because we're just distributing the negative in, and then we do 2x minus 6y. Beautiful. We solve for the derivative. This should be our answer here, actually, right? So it's 3x squared minus 2y, 2x minus 6y, so the answer is B. That's because B is the one that matches the answer we got here. So the answer is B. Yeah, so we just do implicit differentiation. We differentiate, and we rearrange it so our y's and x's, or our dy's on one side, and then we factor out the dy, then we divide it by both sides, and that was a pretty easy one. Okay, how old is Maximum Insight? Maximum Insight is old enough to teach you guys calculus, I guess. God, how much, look at all this stuff we've done so far. Gosh, we've gone so far. All right. Next one, everybody. We are going to be doing question 9 here. Okay. Question 9 is a question that relies on Unit 1 concept that a lot of people actually didn't understand when I originally covered it. It's called removable discontinuity. Now, removable discontinuity as a whole isn't that difficult to say. The idea is that because this question is asking us, for what k value is f continuous at x equals 2? So, sorry, this guy's asking a question in chat. Sorry, quick question for AP Pre-Calculus. Are we going to go through the topics and AP Pre-Calc questions that we'll see on College Board? We will be just going through questions you'll see on the exam on AP Pre-Calculus, but this is calculus, all right? We're not doing that. So anyway, this is a removable discontinuity, and the reason why is because if I plugged in 2 for the denominator here, so if I plugged in 2 minus 2, I'd get a 0 in the denominator, and that's undefined, so I can't do that. But the idea here is, okay, so what value of k now would I have to create that would make f continuous at x equals 2? So, your idea here is that what doesn't care about what could we do to try and figure out because we have 2 here. Sorry, it's hard to describe this. Basically, the idea is we use limits. We use limits because what we do is if we do the limit as x approaches 2 of 2x plus 1 comma x minus 2 all over x minus 2 Obviously, if we were to do direct substitution and plug the 2 in, that would mean we get 0. So we can't do direct substitution. But because it's a removable discontinuity, what we can do, we can just cancel these out because x minus 2 in the numerator and the denominator, these cancel out. Lovely. Because these cancel out, we can go over here. We now have the limit as x approaches 2 of 2x plus 1. Lovely. Can we use direct substitution now? I believe we can, right? Because if we plug in 2 plus 1, we get 4 plus 1, which is 5. And so the answer here is actually just simply 5. Because all we did was set up the limit here because it's a removable discontinuity question for what value of k, because originally it wouldn't have been continuous. Oh my god, you guys can't see that. Originally it wouldn't have been continuous, but it is now going to be continuous because we canceled out the removable discontinuity, and so this value of k would have to be 5. So the answer here is simply 5. Good to know. All right. Here we go. Let's continue. Actually, before I continue, let me read some chat messages because I know I'm not doing anything. Oh, I have a channel member in the chat. Hey, channel member. Nice to see you. I haven't got a lot of channel members, so that's nice to see. Bivionk18. Sorry, I know I'm pronouncing that wrong, but yeah. Guys, just get most of the multiple choice right. You can screw the FRQs that much. Getting partial credit on them is easy. Yeah, so the multiple choice are pretty difficult, so I just want to say that. How do you know to take the limit? Because the removable discontinuity, it's a unit 1 concept, so you kind of have to know the ideas of unit 1, but the idea is that originally this isn't continuous no matter what, but because it is asking us what value it makes f continuous, it is putting us in a separate realm where we have to make this continuous in some way, and the way to do that is with a limit. Let's continue. There is no formula sheet. I'm not sure about that. I'm beyond lost. I'm so bad at remembering what graphs are doing, man. There's going to be a few questions later on, but yeah. I hope you guys are following along in the chat. But yeah, we're going to continue now with the next question. What is k? K is just another function here. It doesn't want to write x because x equals 2, but yeah, the k is just another function here. Okay. The radius of a right circular cylinder is increasing at a rate of 2 units per second. The height of this cylinder is decreasing at a rate of 5 units per second. Which of the following expressions gives us the rate at which the volume of the cylinder is changing with respect to time in terms of the radius r and the height h of the cylinder? Okay, so your idea here is that, first of all, it gives us the volume formula for a cylinder, so that's pretty cool. It's nice to know that this is the part that I think a lot of you are scared about. You don't have to memorize all of the formulas. Like specifically when it comes to volumes and like cross sections, you don't actually need to know the volume formulas because they will provide them for you. Like the volume of the cylinder, I already knew this because of a pre-calculus topic in parametric functions, but knowing this is you don't have to. We already know pi r squared times height. That is the cylinder expression. So we don't even have to know that at the top of our heads, but we are going to have to use it a lot in this question, so we're going to need a lot of space. So first of all, we see it's giving us a few things. So I want to write down, first off, what it is giving us. So the radius of a right cylinder is increasing at a rate of 2 units per second. So the rate of radius is increasing. So we do d, here, I want to write this down in red. dr dt, because that's the radius, dr dt is equal to 2. Lovely. And now the height of the cylinder is decreasing at a rate, so the rate of height. So because it's the rate of height, we get dh dt, the rate of height, is equal to, it says 5, but because it's decreasing, it's going to be a negative 5. Okay, so that's what it gives us in the expression. Now we actually have to solve, which is going to take a second because this is an annoyingly difficult equation to solve. So what is it asking us to solve for? What is the volume is the rate at which the volume of the cylinder is changing with respect to time. So it's asking us to solve for dv dt, the derivative of volume with respect to time. Sorry, that's dv dt is very difficult to say. Okay, So let's write this over here. dv dt would be equal to, well, first of all, we have to find the cylinder expression from earlier. So what I'm going to do is I'm going to take the derivative of this expression right here, the volume that we were given. Now, I'm not going to take the derivative of pi. We're just going to keep that on the outside because that makes it so much easier. So we'll keep pi on the outside, but then we want to take the derivative dv dt of r squared times height h, because that's what's left over here. But we kept pi on the outside there. Okay. So now what would this be equal to? This would be equal to, gosh, d dt of r squared times height plus d dt of r squared r squared times h. Yeah. Sorry, I'm just doing the product rule here. This is the product rule, remember. So we start out with the dv dt. So this is the product rule because r squared times h. So keep the first one the same. Okay, gosh, dang. Sorry, my mind is blank right now. So remember, it's the power rule here. So we do the derivative of the first r squared, then we keep the second the same, then we do plus, do the derivative of the second, we keep the first the same, I should say, sorry, and then we do the derivative of the second. So d dt of h. That is the product rule we just went over. Okay. Okay. Now we can write what all of this is equal to, which would be equal to pi on the outside. So pi is on the outside. And then we can add some like terms here. So what is the derivative of r squared? It is 2r. What is the derivative of h? Well, we don't do the derivative of h because this is the power rule, so we're just plugging stuff in. We do h. We're just simplifying this down. Plus r squared times the derivative of h, which the derivative of h would just be dh dt, right? Plus dh dt, yeah. The derivative of h would just be dh dt. Okay. Now we have simplified this all down. We did the product rule earlier, did this one. Now we have simplified this down. So let's plug in what we're given, because we were given earlier that dh dt is equal to -5. Oh my goodness, I almost forgot, because we did the derivative of this. We have to multiply it by dr dt. The derivative of this, I should say, dr dt. Oh, that's so bad. Yeah, so that's just an implicit differentiation thing because we did the r, so we have to multiply it by the dr dt. Okay, so we are given dr dt and we're given dh dt. So let's actually plug in those values. So we get equal to pi multiplied by 2r, and then we are given dr dt, which is right here, which is 2, plus r squared time plus, then we're dh dt is -5, so actually we're just going to do minus 5. All right. So now that we plugged these in, we can multiply them by one another, I believe. Oh, I did plus here. Oh my goodness, I made a mistake, guys. This should be just multiplied by r squared times the dh dt. So this is multiplied. Sorry, that's the product rule. I just accidentally put a minus down here. I don't know why. Okay, so let's do some simplifying. We get pi is equal to 2r times 2, which is just 4r, plus r squared times 5, which is just 5r squared. And I forgot to bring height down, of course. Height was from here. I am so bad at bringing stuff down. I just realized. And then height comes down here too. Okay, and now we can bring this all the way over here, and we can plug in pi, so we distribute pi into both terms. So we get 4 pi rh, right? Yep, plus pi 5r squared. Oh my god, I can't. R squared. There we go. 5 pi r squared. I hope you can see that. Or 5 is probably going to be in front here. So what do we got here? For this one isn't right. This one isn't right. 4 pi RH minus. Is it minus? No. Oh, it is minus because because this is a -5. I forgot. Oh my gosh. Okay, yeah. So this would actually be a minus here. I am making so many errors in this problem with carrying stuff down. So this is actually a minus, not a plus. And so this one is not the right answer. So it would actually be C. Sorry guys if that was hard to follow. I apologize. This was I did everything correctly. I just did not bring down the variables at all. So yeah, good thing I corrected myself though because we would have got the question wrong. Can you do BC? We're not going to do BC. I apologize. Okay, now we got the next problem. This is summation notation. I know a lot of you probably have not memorized this, so I'm just going to write it down as it is to make it easier for you. You have to memorize this though, so please take the time and memorize this. The integral from a to b of f of x dx is equal to, the summation notation is the limit as n approaches infinity of the sigma. Gotta love this notation. The sigma for k equals 1 with n on the top of f of x sub k and multiplied by delta x. All right, there you go. You have to memorize this formula, guys. I know it's not going to be pleasant, but you do have to memorize it. Okay. We're given the definite integral 2 to 6 of the square root of x. So first I'm going to solve for my delta x. Now there's a other formula for this. I'm not going to write it down because it's a lot, but here, let's actually write this in blue. Delta x is equal to, delta x is equal to b minus a over n, if you remember. So b minus a over n, what is b here? Sorry, 1 second. I'm trying to figure out the b here. So the b is 6 minus a, which is 2. So 6 minus 2 all over n. We don't know what n is. 6 minus 2 is 4 over n. So we know delta x is going to be 4 over n. Now, x sub k, what is that equal to? Well, that one, that was the width, so now we have to do our height. So f of x sub k is equal to a plus k delta x. Okay, which would be equal to, we got to plug in our numbers, 2 plus k. We just figured out delta x was 4 over n. Lovely, just like that. And then we can simplify this down and just put the k in the numerator, so this can be equal to 2 plus 4k over n, just like that. Okay, well now we're given both of our values. We know what they are, so let's plug it into the summation notation. So we get the limit as n approaches infinity of, I'm so bad at writing a sigma, k equals 1, n. So we had f of x sub k. F of x sub k. Sorry, f of x sub k is going to be, well, we have to plug it in. So our original function is the square root of x. So because the sub k is here, we just have to plug it in for x in the original function. So the f of x sub k would be the entire square root because the square root of x. And this is the f of x sub k. So, or it's the x sub k, I should say. So 2 plus 4k over n. Lovely. And then we multiply that by our delta x, which we found out was 4 over n. All right, I believe this is right. I hope it is. So 4 over n on the outside, 2 plus 4k over n. So it can't be this one, can't be this one. 4 over n, 4k over n, 2 plus. Yep, it's C. That's right, it's C. Yes, we did it. I love summation notation. It's so much fun, everybody. Aren't you having fun? Okay. Yep, so you do need to know summation notation. Just remember that, guys. You do need to know summation notation. It's if you're gonna miss a question like this, if you don't know it, just understand this form right here. That's all I knew. I guess I also knew the delta x and x sub k, but just understand it. All right. Okay. What do we got for the next one? The figure above shows a graph of the continuous function g on the interval 0 to 8. Let h be a function defined by h of x is equal to the integral from 3 to x of g of t with respect to time. On what intervals is h increasing? Okay, so sorry, so we are given a function g. So imagine this one. So this function is the integral, meaning it is the prime function, or it is the original function. So even though this function is g, imagine this as being little g, g of x. Imagine this function right here as being big G of x. Or this could also be g prime and then normal g. It's whatever you want to interpret it as. Okay. So the graph here is the derivative. Now, because the graph is the derivative, we have to know what exactly this means. So on what intervals is h increasing? So remember, if an original graph is increasing, that means, if this original graph is increasing, that means, oh my God, you guys can't see that. Sorry, one second. If the original graph is increasing, that means our derivative graph has to be above the has to be above the x-axis, has to be positive. So it just has to be, it can't be down here. It has to be above the x-axis. So if it is an increasing graph, it's above the x-axis. It has to be positive. So if we look on our derivative graph, we have to look at anything that is positive here. So any intervals that it is above the x-axis, well, what we have here, it would be this interval right here and this interval right here. So this is the interval 0 to 2. This is the, or sorry, not 0 to 2, 0 to 1. This is the interval from 3 to 7 right here. Okay. So we looking for 0 to 1 and 3 to 7. Not this one, not this one, this one right here. So the answer is C. Pretty easy. It's a Unit 5 concept, but you just have to understand graphs to know it. Okay. Oh, gosh, this one doesn't look fun. All right. Okay. This is the integral of x. This is u substitution. Oh, I wish everybody luck on this. I don't like u substitution. It takes too much time for me. Okay. So how do we want to start this off? I'm gonna just copy it down. The integral of x over the square root of 1 minus 9x squared dx. Okay. So this is a u substitution problem. The reason it is the u substitution problem is because I would have to use the chain rule if I was trying to differentiate this. So it's a u substitution problem. So the idea when it's a u substitution problem, you got to set u equal to the inside function here. So u is equal to, here, let's do this in a different color. U is equal to the inside function here, which is 1 minus 9x squared. So then we find the derivative du dx, which is equal to, let's see, 2 goes down, so 18 to the 3, or no, wait. Oh, sorry, it's differentiation, so it's, if it goes down, it's subtracted by 1. Okay, so it would be negative 18x. Sorry, my differentiation skills could use some work. And then we get, we can put the x on this side. We can put the dx on this, or sorry, the du on that side. So we can get x prime, or x is equal to, sorry, I mean to say x dx is equal to negative 18x, or not x, negative 18. Cool. All right, so now what we do is we go back to our original expression, this one, and we plug in u. So we get our function. So we're going to put the dx on top just to make this easier for us. So we want to do x dx all over the original function we have, which we can just say is equal to the square root of u now, which is all equal to, we have du on the outside now, du, and we have, okay, yeah, we have x and dx in the numerator. So because we have x and dx, we can actually just plug the x dx, because we figured that out earlier. X dx right here, x dx there. So we know that's negative 18. Oh, I completely forgot the du is over here too. I hope some of you guys caught that. Du is over here too. Yeah, so the x dx du. So we go back and we simplify. So the x dx, we plug in what we got for x dx earlier, which is the negative 18 du all over the derivative, just again, once again, differentiation of u. Lovely. 1/18. Negative 1/18. Oh my god, I'm such an idiot. Because this would be 1/18, wouldn't it? Yeah, because you subtract, divide. I'm sorry, guys. I went too fast on the u substitution. So this would be 1/18 right here. So this would actually just be 1/18, negative 18, the denominator, or the numerator, I mean to say. And then this du cancels out. Okay. So negative 18 du over the square root of u. Thank you guys for following along with me. So we can move the negative 1/18 on the outside because that one's pretty easy. Let's just multiply the numerator. So we can do the integral, but we can, oh gosh, that's a bad integral. We can do the integral, but we can move the negative 1/18 on the outside because remember, that's one of the integral rules. You can move integrals to the outside. And then we get 1/u. Let's say the 1 over square root of u du. Okay, this is simplified too. All right, everybody. Now what we do is we actually have to plug u and u back in. Or actually, I guess we can rearrange it first. So we can get this equal to negative 1/18. I'm going to stop switching colors. It's too much work. This would be equal to u to the 1/2. I'll just make it easier for me to integrate du. And that is equal to negative 1/18. Keep having to write this every time. U to the 1/2 over, or sorry, u to the 2/2 times the u over the 2/2. U to the 3/2, I should say. Because we have to add one, sorry. So it would be equal to u to 3/2 over 3/2. Okay. All right, now we, oh wait, we just have 1, so we can actually just say this is equal to 1/2. Sorry, guys. U to the 1/2. Okay, beautiful. Oh my god, not u to the 1/2. What am I doing? 1/2. Sorry, guys, I apologize. So this is what our u substitution is equal to on the bottom. So now that would be, we don't have the integral anymore, so we can actually just simplify this. So we get equals negative 18, like be negative 1/9 if we simplify with the denominator. 1/2 is multiplying by 2, so we get the square root of u instead to simplify. And then we get negative 1/9 if we plug u back in from earlier, which you guys can't see, of course. If we plug u back in from earlier, we get negative 1/9 is equal to the square root of u, which is 1 minus 9x squared. Just like that. And then is that one of our answers here? Negative 1/9. Oh, and then, of course, we have to add the plus c. I forgot. Plus c at the end. That's a. Cool. That's a. Sorry if that was a little hard to follow, guys. The u substitution is one of my least favorite things to cover, but you do need to know how to do u sub, so just remember that. I apologize if that was a little bit confusing, but we'll continue now. Okay, so shown above is the slope field for which of the following differential equations? Do I need to zoom out on this one, or I can just keep it there, right? Yeah. So the idea for this one, sorry, I gotta change my sheets over here. The idea for this one is that we have, if you'll notice that slopes are constant across the horizontal axis. You see a slope that is constant because this is just a straight line for the slope field. And then you see this one is also constant because it's another just straight line. And because they are constant across horizontally and not vertically, that means everything is going to be with respect to y. So if it's across, not with respect to y, it means it depends on y and not x. And so because it depends on y and not x, that automatically means that c and d, because they have x in our problem, is not going to be the answer. Can't be c, it can't be d. Okay, that's all because of these horizontal lines right here. All right, beautiful. Now, which of the following is a differential equation? So the way I want to do this is really quickly just say that we know that the slopes are equal to 0 at the line. So the slopes equals 0 at the line. This is y equals 2 and y equals -2. So because of that, which one of these problems are going to have zeros that are at 2 and -2? So for our first one, we see that this is a rational function. So we know that zeros of a rational function come from the numerator. So if we solve for the numerator, y minus 2 is equal to 0, we get y is equal to 2. That's the 0. So because -1/2. Oh, it's -1/2. Yeah, you guys might have fixed me earlier. There might have been a -1/2 that I missed here. Oh, yeah, it is. Sorry. Thanks for reminding me, guys. I apologize for doing that one so quick. Okay, y minus 2 equals 0, y equals 2. So our 0 here is 2. So because 2 is our 0, there's only one 0 in this rational function. So we don't have the -2. We don't have the 0 at -2, which the slope field has. So it cannot be question A. It needs the -2. Then dy dx is equal to y squared minus 4 over 4. Now if we solve the numerator here, y squared minus 4 is equal to 0. So we get y squared is equal to 4. And then we get y is equal to square root of each of these, which is equal to 2. Or sorry, we can just do the difference. Oh, wait, we don't even need to go that far. We can just do the difference of 2 squares here, but I guess we could just do plus or minus 2 here. Yeah. So we get y is equal to plus or minus 2. So we get -2 and +2 as our x's. And look at that. We have lines at 2 and -2. So we know because this has our two zeros, this has to be our answer. So this is the thing. I know I didn't cover slope fields that much, but slope fields, your idea is that you have you have horizontal lines or vertical lines. If it is a horizontal line, it is equal to 0. So when you're trying to solve for equations here, we know that a horizontal line is equal to 0. So solve for your zeros in your equations that you're given for multiple choice. And then whichever one has the right zeros is going to be your answer. That is how simple the slope fields are to solve. Okay. Let R be a region bound by the graph x equals e to the y. The vertical line x equals 10 and the horizontal lines y equals 1 and y equals 2. Which of the following gives the area of R? Okay. So let's write down. So we know our regions that it is bounded by. Sorry, I don't want to get it under. So we know our regions that it is bounded by. X equals e to the y. We know x is equal to 10. We know y is equal to 1. Sorry, this looks like a y. Y is equal to 1, and then y is equal to 2. These are bounded areas. So the idea here is this is a Unit 8 topic. So it's kind of the area, if you remember. The formula you're using here is going to be this one. The integral of Jesus Christ, I am so lost right now. So the integral of 1 to 2, because it goes from y1 to y2. So the integral of 1 to 2 of the right minus the left. So the right minus the left, all with respect to x, or with respect to y, actually, it would be in this instant. That would be your formula for you're using here. So let's plug it in. We need to figure out, what our right and left is. Our right here would be x. Our left here would be our right here would be 10, I should say. Our left here would be e to the y, because it's the functions on both sides. So we get the integral of 1 to 2 of r, which is the right. R is going to be 10. And then we do subtract the left, which is equal to e to the y. dy. Oh, my goodness. Okay. Now, of course, we could solve this. We could solve this integral right here, and we could get an answer. But the thing is, it's not asking us to solve for it. It's asking us just to set up an equation. Which of the following gives us the area? So we can solve for the area, sure, but which one gives us the area? So our answer is actually this already. So 1 to 2 of 10 minus e to the y, it's C. That is our final answer. Pretty simple. Okay. Maximum insight, should I take calculus A, B, or BC? I'm an AP pre-calculus right now. You can do, honestly, either or. It doesn't really matter. But yeah. Oh gosh, this is a big one. Okay. The figure shows the graph of f. If f of x is equal to the integral of 2 to x of gt dt, which of the following could be a graph of y equals g of x? So remember, the graph of the figure is done. So g of t is going to be, so this means this graph of f here is the derivative. Derivative. Sorry, I can't spell right now. This is calculus, not English. So the idea here is that we have a constant slope, a slope that is constantly increasing. And whenever you see that, a slope that is constantly increasing, I want you to imagine what a derivative graph will look like. So if we have our f graph of a slope that's constantly increasing, like the one we just saw, our derivative graph, oh my God, you can't see. Our derivative graph, thank you for the $1 pencil fry. The derivative graph is going to be just a straight line. Now, of course, it could be anywhere on the y-axis, but it is just going to be a straight line. Now, because this is just going to be a straight line, it's just because it's a constant slope. And the idea here is that the derivative, because this is a positive slope, it has to be above the x-axis, not below. If it was below the x-axis, then it would, it would be a negative slope if it was below the x-axis, but it's positive slope, so it has to be above the x-axis. So whichever ones here are straight lines are going to be our answer. So it can't be this one, because that is not a straight line. It can't be this one, because it's not a straight line. It can't be this one, because it's not a straight line. All right. Oh, why did I call it the derivative graph? I'm sorry, guys. I'm just not doing it. So this isn't our derivative graph. This is our original graph. Original graph. Original graph. So this is our original graph right here. Our derivative graph is our original. Oh my gosh, this is so difficult. So the one we're trying to find is our derivative. Okay. So original derivative. That's why it can't be these, because these are not straight lines. Remember, our derivative graph is going to be a straight line if we have a constant slope. So A and B are going to be our answers. So which one is which? Can't be this one. Why can't it be this one? Because the graph ends at the y-axis. Can't be this one. So it has to be this one right here. It has to be this one, A. Beautiful. Okay. I apologize. I did some misinformation there, so I'll just restate it. The graph of f is the integral, the original expression, and we're trying to find y equals g of x, which would have been our derivative. So just remember that. This would be these graphs are derivative graphs we're trying to find. Okay, thank you guys for sticking with me. The line y equals 5 is a horizontal asymptote to the graph of which of the following functions? Okay, this is interesting that we are doing this in calculus, because this is actually a pre-calculus topic. This is vertical functions. If you remember, a horizontal asymptote goes by bottom heavy, top heavy. So, or top heavy functions, if the numerator has a bigger degree than the denominator. So that's so bad. If we had, oh my God, if we had x squared all over x, because the numerator is a higher degree, it is a top-heavy function. That means that there is not going to be a horizontal asymptote. There is going to be a slant or oblique asymptote. So it can't. So you're probably not going to see any horizontal asymptotes in this equation. So basically, if a function is bottom-heavy, if the degree on the bottom is bigger than the degree on top, so the degree on bottom, that means there's going to be one horizontal asymptote. It's going to be at y equals 0. So automatically y equals 5. So if you see any bottom heavy functions, it's not going to be y equals 5. So let's see here. This one is bottom heavy because we have x and no x in this. This is x to the 1. There's no x up there, so can't be c. Same heavy, same heavy. This is same heavy. So this one is, we don't have any division. This is just a polynomial function, so it has no horizontal asymptotes because it's polynomial, so it can't be this one. All right, so if the degrees are the same, if it is x to the 1 over x to the 1, if the degrees are the same, it is going to be a ratio of the leading coefficients. So let's say we have 2x to the 1 over x to the... So this would be equal to, the horizontal asymptote is y equals 2 over 1. So if they are same heavy, it is leading coefficient over leading coefficient. So for this one, the y equals sine of 5x over x. If you remember trigonometry, this one's pretty simple. There's a horizontal asymptote at y equals 0. So that's why it can't be this one. That's just trigonometry basic stuff. Y equals 5x over 1. So our leading coefficient is 5x, and this is our bottom one. So 5, you can imagine an invisible 1 here. So it's 5 over 1, which is just equal to 5. So y equals 5. That's our line. Y equals 5. So it is D, but let's check C really quick, just so I can show you. Our leading coefficients here are 20x squared and 4x. So 20 over 4 is equal to 5. Oh, but look at this. We have 2y equals 5. Now, I solved this incorrectly for a reason, because I made a common mistake. Notice how this is 5 over x, but there is a negative sign here. That negative sign means it is a negative 1 instead of a positive 1. So 5 over negative 1 is equal to negative 5. So y equals negative 5 is not this one, so it cannot be D, which means our answer here is actually E. D is trying to trick you, but our answer here is actually E. Okay. Oh my God, we get to use a calculator. No way, guys. How are we doing? No way we get to use a calculator. That's so cool. I'm so happy that we get to use a calculator. All right, I have to get a calculator to appear on the screen though. So, bam, calculator appeared. I was told that you guys get to use Desmos on your exam. I don't know. Listen, I hear a lot of information. I'm not going to try and guess if everything is true. I'm sure you get to use Desmos. Can you guys tell me in the chat, actually, do you guys get to use Desmos on your exam? Calc is short for calculator, by the way. Thank you. I appreciate. Guessing ahead without using a calculator. You do get to use Desmos on your exam? Okay. Well, I'm going to be using a TI-84 calculator here, only because it's just easier for me to do it. But if you need to use you can use Desmos just as well. It will work totally fine. But the TI-84 is more standard. It's the way I learned, so I'm going to show you how to do it on there. Okay, so honey is poured through a funnel at a rate of R of t is equal to this function right here, ounces per minute, where t is measured in minutes. How many ounces of honey are poured through the funnel at time t equals 0 to t equals 3? Okay, so let's set up our integral here, because it is asking us the integral from time equals 0 to time equals 3, and then it is just of this function right here. So 4e to the negative 0.35 t. And then, of course, that's with respect to, it would be t in this instant, right? dt. So let's take our calculator and plug this in, because this is an integral. Yes, we could try and solve it on our lonesome. I don't want to, though. So let us use this Banpita. I have moderator Banpita if you want to. All right, you know what? Fine, whatever. Pita, you're being put in timeout. Haha, because I can do that. Good luck. Okay, moderator, step up your game, man. I do have a mod in the chat. So anyway, so if you remember, the way to get an integral is to go to your math button here. It's to scroll all the way down. You have derivative here at number 8. Math number 9, though, is going to be your integral. This is why Desmos might not be that useful. So you get your integral, and then we say the integral from 3, 0, 2, 3 of the function 4 times second e to the negative 0.35 x with respect to x. Now, I know you might notice that I did x instead of t here because we had t in the original one. The reason I did x is because you don't actually need to know, it doesn't matter the variable necessarily. You just need to solve this. So because the derivative on top here was x, I just did with respect to x. So you just have to make sure the variables are the same. So we we get 7.429. 7.429, that is answer number D. So D is going to be our answer. So pretty easy with a calculator. We can just solve the integral. So make sure to abuse your calculator when you have it. Let's move the calculator back here so we can answer the question. Beautiful. All right. Let f be a derivative defined by f prime of x equals 2 plus 2x minus 8 sine of x plus 3. How many points of inflection does the graph have of f have on the interval 0 to 9? All right. So, man, this is going to be fun. So if you remember, points of inflection occur at in the second derivative where the second derivative is equal to 0. So, but this is the first derivative. We're asking how many points of inflection does the original function f have if we are only given the derivative function that we have here. So, you have to remember some stuff from Unit 5 here. And that is that points of inflection, so points of inflection, all are going to occur where the derivative has local maximums, maxes, and mins. So what I want to do is I'm going to graph this on either Desmos or my graphing calculator, and I'm going to count the amount of local maximums and minimums between the intervals 0 to 9. So let's head on over to our graphing calculator again. We have the function f prime of x is equal to 2 plus, remember your calculator needs to be in radians mode for this too, 2x minus 8. 2x minus 8 sine of x plus 3. I really hope this calculator is in radians mode. I actually didn't check. X plus 3. Okay, so we get that function. Now let's look at the graph of this. Oh gosh, that's a fun graph. Okay, so let's shrink our window down. We only need to know the interval 0 to 9. So let's type in x minimum to be 0, our x maximum to be 9, and then why don't we put our y maximum to be like 15 and our y minimum to be 0. Let's try that out, see how that goes. Okay, we don't see the full graph, so we need to make our y minimum a little lower. Y minimum, why don't we put that in -10? There we go. All right, so remember, now we count the amount of local maximums and minimums. So we have 1, we have 2, we have 3, and we have 4. I count 4 here. Do you guys count it? 1, 2, 3, 4. Now the other way you could do this is you could solve for f double prime and find what the where everything is equal to 0, find the zeros of the graph. That's just a lot of work. Let's not do that. Let's find local maximums and minimums. So 1, 2, 3, 4. So there is 4 points of inflection across this interval. So let's remove my calculator real quick. We have 4. So our answer is D. Lovely. Okay. Next one. This is our second to last one, right? Yeah. Oh my God. This stream has flown by so fast. Okay. The graph of the function f is shown in the figure above. Which of the following values of x is f prime positive and increasing? Okay, so let's imagine this. If f prime of x is positive, so greater than 0, if f prime of x is positive, that means that the f graph is going to be rising. So f is going to be rising. Okay. If f prime, because positive and increasing, so if f prime of x is increasing, f prime of x increasing means that f double prime of x is greater than 0. Or f double prime of x is going to be positive, greater than 0. Which inherently means that f is going to be concave up. To be concave up. Okay, good to know. So f needs to be concave up and rising. So let's look at our points. A, f is concave down and not rising, so it cannot be A. B, f is rising, but it is concave down, so it can't be that. Or sorry, B is just kind of 0 here. It's at that vertical tangent there, so it can't be B. C, f is concave. X is rising, but it is concave down, so it can't be C. D, f is concave up, but it is decreasing. It's not rising, so it can't be D. That means already by process of elimination it's E, but let's take a look. E is already concave up, and it is rising, so we know it has to be E. E. Lovely jubbly. All right, guys, it's our last question. Do I need to zoom out? I think I need to zoom out. Yeah, that should do it. Okay, we will go over this in just a second. Oh, I just realized we didn't have to even use a calculator for this question. Even though it's the calculator question, we didn't have to use it. That's nice. All right. Well, what you could also do is just go on your calculator and confirm this stuff. Like, if you don't remember the Unit 5 stuff, if like how the derivative relates to the original function or the second derivative, you could test stuff on your calculator with derivative functions and stuff and see. But yeah. Anyway, let's read the chat. We only have one more question left, so let's read the chat. How are we doing, guys? Okay. Well, easy for last. Yeah, it does look pretty easy. Bro, you need to zoom in. Is that okay, sorry. I'm zoomed in. Don't you worry about it. Are you doing a pre-calculus live? Yes, tomorrow I am doing AP pre-calculus. Okay, Max, any FRQ predictions for tomorrow? No clue. Good luck. I tried to give an FRQ prediction for AP US history when I did that live stream. I got it completely wrong, so don't listen to me. We're alive. This is the hardest question on the exam. All right, let's just do it really quickly. All right, the graph of f is shown in the figure above. The value of the limit as x approaches 1 from the, is that the left or right? Okay, this guy is right. I did need to zoom in. That is from the right. That is a plus, not a minus. Okay, so it's from the right. So the graph, so as x approaches from 1 from the right, so we go on this side, it would be approaching 2. Let's see. Easy one for last. All right, gosh. It's not going to be this filled in dot because that's not where the graph approaches. But if we were to ask what f of 1 is, that would equal the filled in dot, not these two holes. So it would be f of 1 is equal to -1. But that's not the question. It's as x approaches from the right. If we were going from the left, it would be -2. All right, guys. That is my whole practice exam. Wow, I got through this unit so fast. I can't believe how fast we got through that. So it is obviously the night before your exam. It's currently 5 p.m. for me, 7 p.m. for all you guys on the East Coast, and I guess it's only 4 p.m. for you guys in the Pacific. But what do you guys got? What do you guys want me to cover? We can go over some U substitutions, some derivative functions. What time tomorrow? If you need to tune into my live streams tomorrow, I'm doing AP Psychology at 5 p.m. EST, or if you're on the Pacific Coast, that would be, I guess that's 2 p.m., right? Yeah, 2 p.m. on the Pacific. If you are wanting to do AP Pre-Calculus with me tomorrow, or wait, what were my times I announced? Sorry, I don't remember the times I announced. Let's see here. Sorry, guys. I don't remember the times I announced at all. Yeah, so AP Psychology is going to be at 5 p.m. EST tomorrow. AP Pre-Calculus is at 8 p.m. EST. If you live in the mountains, that's 6 p.m. or 3 p.m. You guys will figure it out. Just check my Instagram or my YouTube post. You can see. Okay, please, can we go over question 8? Question 8, which one was that? The U substitution one? I'm not going to rewrite all my work, but I can explain how I got there. X over the square root of 1 minus 9x squared dx. So we had to set the inside function, the u sub to this one. We did du over dx is equal to -18x because that is our derivative function. That's our derivative function. Then what we did is we brought the x over to this side, and we brought the du over to this side, which had to turn this into 1 over -18. So then we did our derivative function over here, the dx. We didn't actually need the du here. That's an incorrect statement. Then we simplified it. We plugged our dx back, our x dx here, -1 over 18 in, and we did u. And then we solved for our integral right here, and then we actually solved again. negative 1 over 2. This would be negative again. And then divide by a 1 over 2 just means you're multiplying. So these would cancel out. That's why we get the square root of u here. And then negative 1 over 9, just like that. And then this is, yeah, it's just hard to explain. But you got it. We'll go over some more u sub if you guys want to. Let's see, what do we got? I thought it was negative 1 over 2, negative 1 over 2, yeah. But we corrected it to negative 1 over 2. We got it. Okay, imagine the actual test has easy MCQs. I thought these ones were pretty easy. They weren't that bad. I mean, like this one. Can you go over units 8 and unit 7 practice MCQs? I think I already went over some at the start of the stream. You can rewatch that part if you want to. Oh my goodness, yes. Did we ever finish that problem we were stuck on earlier? No, we didn't. I can actually go back to that. Sorry, we'll go here. Hi guys. So we never finished that problem we were stuck on earlier. I'm so sorry that I never finished this problem, but I want to figure out how to do it. So give me 1 second. I'm gonna go back to that problem. Okay. Give me 1 second. I just got to switch over the screen here. On this one. Okay. So this is, oh, sorry, I need to present. Hold on. Sorry, you guys can't see this, can you? Okay, this is the one we were stuck on earlier. Thank you guys so much for, oh yeah, by the way, thank you for friends for the 199. I appreciate it. I already went over MCQs in my past, but in the past of this video, unit 7 and 8, so feel free to rewind the video if you like. So this is one we were stuck on earlier, and I think, honestly, I was just doing too much. If we're going to be real for a second, I think I was just doing too much because the general solution here, if you remember, sorry, let me grab this. So we had a bacteria colony grows at a rate with 500 bacteria and grows at a rate proportional to its current population. After 3 hours, there are 2,000 bacteria. Find the population as a function of time. Okay, so remember, all exponential functions, differential equations, are modeled as dp dt. Or sorry, not dp dt, but dp dt, the derivative of population with respect to time. And then all of them are modeled with some constant k times the variable here, which we said was p. This could also be x, could also be whatever. Doesn't matter. All right. So the idea is the general solution, the integral, the general solution to any derivative exponential function like this, kp, is going to be p of t is equal to kect. Remember, ce to the kt. Kect. That's how I remember it. So if we go back, we take the integral of this, the general solution is going to be this, ce to the kt. Now, here's what we know. We know that after the colony starts at 500 bacteria, so p of 0 is equal to 500. That's what we know. So we are given the point, what would that be, 0, 500, yeah, 0, 500. So we already know this is our general solution. We trust we know that. So let's plug in this point that we have here, 0, 500. So we get 0. Oh, wait, no, sorry, it wouldn't be 0. It would be 5. Oh, my gosh. What the heck just happened? Why did that delete? Oh, my God. What the heck happened? No, you guys can't see this. No, I deleted everything. That's so sad. What did I just do? I just deleted the problem. All right, I'm going to have to will it back into existence. I'm sorry, guys. I can't believe that just happened. And we were doing so good, too. I actually understood it for once. Sorry, 1 second. I can't believe I just deleted that. I'm so bad at live streaming. Watch my videos, not my streams. Okay. I can't delete, so I have to do this. dp p p p p of t kect. It sounds wrong, but it's correct. And then we were given the point 0, 500. Okay, so now we plug in 500. So to this problem right here, So we do 500. Here, let's change the color. Don't. But Canva, you can't Control Z, which is what I was doing on the PDF, which is really nice. We'll do purple. How does that sound? 500 is equal to, we are given the original point. So we don't know C. We do know E here because E is just E. To the 0, because 0 times T is just going to be 0. So C e to the 0. E to the 0, anything to the power of 0 is 1. So that means C is going to be equal to 500. Lovely. All right. That means that we have, if we plug this back into our original function here, that means P of T, because we just solved for C, P of T is equal to 500 E to the KT. So now we are also given another point, and that is 3, 2000. This one, 3, 2000. So because we are given this other point, we can actually plug in more numbers. Don't you love plugging stuff in? So we'll use blue this time. We're gonna plug it into this one. So 2000 is equal to 500E to the 3K. Okay. So now that we are given our 3K here, we do 2,500E to the 3K. So we divide the 500, we get 4 is equal to 3E to the 3K. Lovely. And then the way to get rid of this E is to take the natural log of both sides. So we do the natural log of, it's not absolute value, natural log of 4 is equal to the natural log of E, which just cancels out that E, which is going to just be equal to 3K. The natural log of 4, I'm not going to do that in my head, but we don't have to. We just need to solve for K. So K is equal to the natural log of 4 all over 3 because we divided the 3. And you guys can barely see that, can you? All right. I'm just going to get rid of my camera here. Okay. So this is what we were given. So now we have solved for K and C. So our answer here is actually just to plug it into our original CE to the power of KT. So our answer is going to be K, or P of T is equal to 500, which was C, times 4. Yep, 4. Because it's at the current population. There are 2,000 bacteria. Find the population as a function of time. So 4 to the T over 3. That means every 3 hours, the population multiplies times 4. If you're unsure of, oh my gosh, yep, that's all right. I deleted everything, but that's what that is. That's how you do that. Thank you guys. Sorry if that was a little bit complex. Oh my god, you can't see that. All right, I hope you guys understand. It is not. What is optimization? Search it up on my APUSH unit or my AP Calculus Unit 5 video. I have a optimization that I do there. Okay. Can you do some word problems? Oh, wait. Stream is not over. Sorry. I don't know why that's there. Actually, stream is kind of over. All right, guys. I just want to mention that I'm not going to be going over any specific practice problems or anything now. So that's why I will try to, but the stream is mostly over for like actual going over planned concepts like the AB exam. I will go over problems if you guys need to, anything like that. But just know that if you don't have to stay here. You don't have to stay shackled to this stream at all. There is not really much that's going to keep going on here. I'll be reading chat. I'll be answering any questions you guys have. But yeah, if you want to click off now, you're totally free to. Feel free to go watch my videos. Good luck on that exam tomorrow. But yeah, let's see here. It is over because that's all I had planned, the AB. All I had planned was the AB practice exam and the Unit 7, which honestly took a shorter amount of time than I thought. But yeah, do you guys need me to re-go over anything? We can go over some chain rule stuff if you want to. We can go over some use substitution problems if you want to. I just want to make sure all you guys are ready for this exam that's coming up tomorrow. So please just let me know if you guys want to go over anything. What do you guys got in the chat? How high is the curve? I'm told it's like a 65% you have to get if you want to get a 5, which is like a D. So 65%. Unit 6, is this pre-calculus now? No, it is not. Pre-calculus is tomorrow. I'll see you tomorrow. Please do an FRQ. Yes, please go over the chain rule. Okay, we can go over the chain rule. I mean, the basic thing with the chain rule. Sorry, let me get a problem up because I have a document here. Trying to find this. We'll go over a chain rule problem just to help you guys out. Write this down. Okay. Oh my gosh, my face is gone. What happened to my face? There I am. We're going to go over the function. So imagine if you're given something like this. dx of 3x squared plus 1 the fifth. The idea here with the chain rule is that you have to first, you have an inside function, you have an outer function. So you have to first take the, you have to use the power rule on this full thing. So this would be equal to 5. So we use the power rule on the whole thing. We keep the inside function the same, 3x squared plus 1. And then we subtract the power by 1 because of the power rule. So that's 4. And then we multiply it by the derivative of the inside function. So 2 times 3 is 6. And then we subtract the power by 1. So it would be 6x. We multiply it by the 6x. We can multiply that 6x by the 5. So we get 30x is equal, or sorry, multiply it times 3x squared plus 1 the fourth. This would be our answer for this chain rule problem right here. Let's move on to another one. Find dx of e to the x to the second. Yeah, the second minus 4x. Okay. So if we were to solve for this one, our chain inside function here is going to be e to the u. But remember, the derivative d dx of e to the x is just e to the x. So the chain rule is a little bit different here. So first of all, we need to we need to write this the same way. Remember, the derivative of e to the x is e to the x, so we keep the inner function the same. So e to the x squared minus 4x. This is technically this differentiated, but then we have to multiply by the derivative of the inside function, which is this 2x minus x squared minus 4x. So we have to multiply by the 2x minus, what would be 4 minus 4. That would be our answer. Can we simplify this down? Let's see. I guess all we would really do is just put the 2x minus 4 up front. And then we would do just the e to the x squared minus 4x. This is the answer for this chain rule right here. This is the answer. All right. What else do you guys want to go over? Unit 6 was requested. You see, I have a video for Unit 6 on my channel that's really good, so we don't necessarily need to go over it. I mean, we can go over specific forms if you'd like. Like, sorry, 1 second. Bring it back to my face. Ooh. Sorry, I'm deleting all this stuff that we just did with the chain rule. I hope this is exhilarating content, watching my face as I talk into this $400 microphone. There we go. We're back here. So, sorry, I want to get my correct notation up here. So I told you before, one thing you guys oh my gosh. I told you before that one thing you guys have to know is summation notation for a definite integral. Now, remember, we're going to go over this again because I just want to make sure that you guys got this. This is a Unit 6 concept, so everybody's talking about Unit 6, just remember. This is too big. The integral of a to b of f of x can be represented by the function. The summation notation, the limit, as n approaches infinity, of the sigma, which is very hard to write. There you go. Of the sigma of k equals 1 with the n on top. Remember, k is just the counter here. Is the coefficient. F of x sub k of delta x. Now, if you're wondering what each of these equal, x sub k is equal to a plus k delta x. If you were wondering what delta x is equal to, it is equal to b, or that's a 6, b minus a over n. This is your summation notation for a definite integral. So if you ever need to convert between these two forms, just know this is the one you have to know, and you also have to know how to solve for these ones too. All right. What else do you guys want to cover? Can we get maximum inside a girlfriend already? Time that guy out for a minute, please. These are so easy. Yep. Okay. I'll just take 0 points on questions like these. Just to remember the summation notation. This isn't that bad. Are your unit reviews and a live stream enough for a 5? I took self-study and I'm going to be using your videos live stream only to prepare. I don't know, only to prepare is the best thing. I only have units, sorry, I'll change here. I only have units 1 to 6 on my AP or on my YouTube channel because I ran out of time to finish the rest of the units. Units 1 to 6, I think if you watch those videos, those are good enough for those videos. Units 7 to 8, I only went over a few concepts, the separation of variables stuff. You definitely would probably want to solve stuff or watch other videos for units 7 and 8. But yeah, I just want you to know that. I will cover another separation of variables problem for you guys though, just to help you guys out. So let me delete all this really quick. I know you guys can't see the screen. Give me 1 second. I'm deleting the summation notation we did earlier. Okay. So this time we are going to do the integral, not the integral. Where's my marker? This time we are going to do this one. dy dx is equal to 3xy. Now, if you want to know how to solve this, the easiest way here is something called separation of variables. Now, you can also do something called Euler's method, but that is a BC only topic, so we are not covering Euler's method. I call it Euler's method. I guess it doesn't really matter. So anyway, we have to rearrange stuff on both sides. Now I'm not going to do every part of it because I already know this is going to be, here I'm going to switch this actually color to be 1 over y. So I'm moving all the y's on one side, so dy. And because we multiplied both sides by 1 over y, which cancels it on this side, brings it on this side. Then we multiply this side, and we get dx on this side by multiplying, so we get 3x dx. Lovely. Now we actually take the integral of both of these terms, because once we have the variables on one side, we take the integral of both these terms. We get this one is going to be equal to the natural log of y, absolute value signs, remember, which is equal to, what's the integral of this? 3x squared over 2, 3x squared over 2, and then plus c. Now remember, there's technically a plus c on this side too, but because we have 2 plus c's, like this is a 1 plus c, this is another plus c, so you use 2 different constants, but because we have 2 sides, we could just move the plus c onto one side and it works just as well. So remember, the way to get rid of a natural log is to put e under it, so e raised to that, or have the natural log be the exponent of e. That's probably a better way to explain it. We go e And then what we want to do to one side, we have to do to the other. So e to this one too. So that cancels out the natural log. And so we get the natural log, or sorry, the absolute value of y is equal to e to the c. We just put the e to the c first, but it doesn't really matter. Or sorry, here. Probably should do this. 3x squared over 2 plus c. Now, we're going to bring this all the way up here. Now, this is equal to still the absolute value of y. But this would be equal to, remember, the product rule of exponents says that we can separate these two into two exponents multiplying by one another. So we'll put e to the c first. E to the c times e to the 3x squared. Oh, you guys, I'll shrink my thing. 3x squared over 2. Now, to get rid of an absolute value sign, we have to do plus or minus on both sides. So we do plus or minus on this side. We have to do plus or minus on this side. So we get y is equal to plus or minus e to the c times e to the 3x squared over 2. I want you to notice something here. Plus or minus e to the c, that is just an arbitrary constant. We don't know what it is, but it can be represented as just one constant. It doesn't have to be plus or minus e to the c. So we get y equals plus or minus e to the c will all absorb into one constant that we'll call c. It's not the same as this constant, this one or this one or this one. It's a different constant, c. So you could probably say this is c. This is c1. This is c1 or whatever. It doesn't matter. This is a different constant. This is c2 or whatever. And then multiplied by e to the 3x squared over 2. And this right here is going to be our final answer. This is what separation of variables are. This is a Unit 7 topic that I never covered. All right, what else? Beautiful. I'm going to fail this test. No, you aren't. Have faith in yourself, guys. I believe in you all. Sorry, I'm going to delete all this really quick. Is there any problems on the practice in the description you guys want me to re-go over? Or is there any specific concepts you want to go over, like U substitution? Or maybe we could go over Riemann sums. Or maybe we can go over, I don't know, inverse derivatives in total. Maybe trig derivatives. Whatever you guys want to go over, we'll go over right now. Please tell me in the chat. I'm going to have my exam in less than an hour, lol. I'm not sure how that works, but okay. I'm going to get a solid 2 and possibly a 3. You guys are going to get 5s. Come on, I believe in you. Optimization, please. I really would prefer not to go over an optimization problem if possible. Cross sections, U sub, disk and washer method. How do you do slope fields if the slope field doesn't have asymptote lines? You can kind of imagine the behavior of the graph, because like if we went back to, sorry, give me 1 second. We'll do U sub in a second, guys. So if we go back to this example right here, where we had this slope field, one of the things that we can see is the behavior of the graph. So technically, we don't have any horizontal asymptote lines here, but what I can do is I can kind of imagine the behavior of the graph. So the behavior of the graph is going to be, say we had a point like right here. If we had a point right here, then we can imagine the behavior of the graph. If we kind of follow the flow or the current of the graph, we can kind of imagine it goes here, and then it comes back up like that. This would be what the original graph looks like. Or if we had a point like here, we can follow the behavior of the graph. So we go down, down, something like that. Oh, those are horrible lines, but you get the idea. So, and then look at the original equation it gives you. Like if it says like one option is, what if the original function is y equals x? Well, obviously this isn't gonna, oh my gosh, you can't see that. What if the original function is y equals x? Well, it can't be y equals x because you have to, this is a quadratic, or not a quadratic, but you get the idea. It's a function that opens up like that. So it can't be y equals x, which would just be this. That's so bad. I can't draw straight lines on a mouse and keyboard. I'm sorry, guys. That's how you use slope fields. Cross sections and Riemann sums, please. Why is the volume lower now? I'm sorry, I might just be away from my mic. I hope that's better for you guys. velocity, position, and acceleration problems would be really helpful in this review. That is a good point. I probably should have put a few of them. Let's see if I can actually snag one. I think I have a few left over from my Unit 4 when I did that. Let me see if I can find some for you. Problem. Okay. Let me really quickly write this down in Canva really quick so I can get you guys. We're going to do a velocity and acceleration problem, which is probably what you're going to see a lot on the AP exam. So this is probably good that we're doing this. Okay, let's see if I can get copied down really quick. All right, this will take 1 second, guys. Acceleration, where's my equations? Thank you guys for waiting so patiently. How are we feeling about the exam tomorrow? I know it's stress, but if you guys can get through it, that would be ideal. T equals 6.4. Ideal. My motivational, I clearly give the best motivational speeches, as you can tell. Given B of 0, 3, and S of to 5 and position functions. Okay. Position function. All right. See if I can do this. All right. Here we go. So we have the velocity and position problem. So your idea here, a particle moves along a line with acceleration, which is by the line here, a of t is equal to 6t minus 4. Now the idea is, given v of 0 is equal to 3 and s of 0 is equal to 5, find the velocity and position function. So let's first write down what we know. So we know originally that s of t is our position function. Sorry, I need to rewrite this. So we know already that s of t is our position function. Now we also know that s of t is equal to s prime of t is equal to v of t. That is our velocity function. Now, what is this also equal to? S double prime of t would be equal to v prime of t or a of t. You might question, how do we find the exact functions here? If the velocity function, if a of t is equal to 6t minus 4, then we also can just write this as v prime of t, because that's equal to, the acceleration is equal to 6t minus 4. Lovely. Okay, so now to find the original acceleration problem, we have to we have to do that. We have to take the integral. So we take the integral of 6t minus 4 with respect to time, and then we get v of t. V of t, the original velocity problem, is equal to, what would that be? 6t, this would be equal to 6t squared all over 2 minus 4t plus c. And we can do some simplifying here. We get v of t is equal to 6 over 2 is just 3, so 3t squared minus 4t and plus c. But we're actually given a point here. V of 0 is equal to 3. So we can really quickly just plug that in. Use the initial condition. So we have the point 0, 3. We can plug that into this one. So we get v of t is equal to, or what would it be? It would be 3 is equal to 3, 0 squared minus 4 times 0 plus c. And this would be equal to 0. This would be equal to 0. So we get c is equal to 3. Lovely. So our velocity function becomes v of t is equal to this one right here, this one with the plus c, which was 3. So 3t squared minus 4t plus, those look like two pluses, Oh my god, what just happened? I just lost all my progress again. Okay, well, we're just going to continue. I have it written down over here. 3t, so the velocity function we figured out just now. I hope you guys were following it because I don't want to rewrite it down. The velocity function we just figured out was v of t is equal to 3t squared minus 4t plus 3. These look like pluses. 4t plus 3. Okay. I can't believe I keep losing my progress. So s prime of t, if you remember, s prime of t is equal to v of t. So because we know that, we have to, once again, take the integral with respect of time. So we've taken the integral once, we have to do it again. So what do we get? We get 3t to the second. So it would be 3t to the third all over 3 minus 4t to the second over 2. 4t to the second all over 2 plus 3t, or yeah, just 3t. Yeah. T, do some simplifying here. 3 over 3 is 1, so it's just t cubed minus 4 over 2 is 2, so 2t squared plus 3t. Okay, this would also be plus c. Can't forget the plus c. All right, then we are given another point, 0, 5 for the s of t function, 0, 5. So once again, we plug in this initial condition. So we get 5 is equal to 0 cubed minus 2 times 0 squared plus 3 times 0 plus c. Okay, this is 0, this is 0, this is 0. So c is equal to 5. C is equal to 5, just like that. And because c is equal to 5, we can now write our original function here, but we can put it with the, we can write our original function here, but we can add the c. So we get, as our final answer, s of t is equal to t cubed minus 2t squared plus 3t. And then plus c, which we know is now 5. I'm sorry, I know these t's and pluses look very similar. I'm trying my best not to make them that way. But anyway, this is our final answer to this problem, guys. Find the velocity and position functions. We found the velocity function was up here. We found the two functions there. All right, thank you guys for sticking with me. I apologize I deleted all my work. Okay. Sorry, 1 second. All right, guys, what are we doing here? What would you guys like to do? Do number 11 on the practice. Okay, what is number 11? Let me switch back to my face so I can do this. Are we dead ass? Somebody asked for number 11 on the practice. Wait, are we talking about this 11 right here? This easy 11? Or wait, is there another number 11 on here? No, there isn't. There is no other 11. This guy is trolling. We're not doing number... Well, I guess I jest. Number 11 might be difficult for some people. So let's just really quickly... Remember, this one is the limit as x approaches 1 from the right. So we go in from the right side, and the part we are approaching is this 2 here. It doesn't matter that we have the filled in dot at -1, because like I said, if it's f of 1, that would equal -1, but it is an f of 1. It's the limit as x approaches 1 from the right. So as going in from the right, we approach 2. Lovely. What's next? FRQ. Maybe. I need to actually pull one off the AP website if I want to do that. But maybe I can find one. Yippee 3. Okay. All right, guys. Would you guys like me to go over an FRQ before I end this stream? Do you guys like me to go over an FRQ? I hope that was I hope the whole test was limits. I hope it is too, honestly. Let me pull up an FRQ. I'm gonna pull up an AP Calculus past exam. AP Calculus past exams. Let's see. It only has 2025, 2024, and 2023. Let's do the one from 2023. Let's see if I can import it over. Good God. Looks complex. 1 second, guys. Sorry. Okay. All right, give me 1 second, guys. We will get to an FRQ in just a minute. And then after that, I'm going to promptly end the stream. Give me 1 second here, guys. Thank you for your patience. I appreciate it. Did we capture? Thank you guys for your patience. Sorry, I'm having trouble with the formatting thing here. Okay, 1 second. Thank you for your patience. I will be just another second. Using the incorrect meaning to interpret, use the right Raymond sum of 3 subintervals. So I have this one. It's the 2023 exam that was taken. And a lot of FRQs are going to be similar year on year because it's the same format. My issue here is there's not really any space to do my answer. There's not really any space to like do my work. I mean, I'll try my best. Maybe I can like zoom in like a lot and just like maybe. Would this work? If I'm just given a full white part. I guess this could work. 6x. Yeah, why not? All right. Let's try it that way. Okay, so here we are. We're going to do this FRQ1 here. So we are given a table. We have seconds and gallons per seconds. A customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differentiable function f, where f of t is measured in gallons per f of t is measured in gallons per second and t is measured in seconds since pumping began. Selected values on f of t are given in the table. Using correct units, interpret the meaning of the integral of 60 to 135 in the context of this problem using use a Wright-Raymond sum with three subintervals to approximate the value of 60 to 135, the integral there. Okay, a Wright-Raymond sum. So a Wright-Raymond sum, is this a calculator FRQ? I probably should have looked. A graphing calculator is required for these questions. Okay, so this is a calculator FRQ. Why did we not do the non-calculator one? I don't know. Okay, so this is a calculator one, so I get to pull out my handy calculator if I want to use it. So basically what we want to do is, it's a Wright-Raymond sum, so that means we are going to type in a lot of numbers here. So the Wright-Raymond sums are these ones to approximate the value of 60 to 135. So we want to take the right points of each of these intervals. So first of all, for a Wright-Raymond sum, we have to write the minus on each of them. So the second term minus the first term. So we do 90 minus 60. And then we have to multiply that by the right endpoint. So f of 90, because we have to find the y. And then we add, because we're approximating the accumulation of change, so we're adding everything. We do the second minus the first, 120 minus 90, all multiplied by the right endpoint because the Wright-Raymond sum, so f of 120. Am I pronouncing Raymond sum correctly, by the way, chat? Any English speakers in here that can tell me if I'm pronouncing it correctly? Plus, and then we do 130, 0.15. So point 15. Plus, here, why don't we just do this all in a different color? Sorry, make this easier. 30 times f of 90. So where does f equal 90? At 0.15. So 0.15 plus 120 minus 90 is 30 again. Times f of 120, which is 0.1. And then we do plus again. 135 minus 120 is that 15? Yeah, it is. 15. And then we multiply that by f of 135, which is 0.05. Okay. So now that we are given this, I wonder if I can do this in my head. No, there's no chance. There is no chance at all. All right, I'm not going to put my calculator on the screen, but basically you just evaluate each of these. So 30 times 0.15 is... I put out my calculator, sorry. It is 4.5. So we get 4.5. 4.5 plus 0.01. That's just 3. So we do plus 3. This is simplifying these. And then 15 times 0.0005. What is that? 0.005. That would be 0.75. So 0.75. So we do plus 0.75. If we were to add all those together, 4.5, 7.5, 0.25, it would be equal to 8.25 gallons. All right, I think that's right. Yeah. So we used a Wright-Raymond sum to approximate it. That would be our answer for A. All right. Must there exist a value of C for the interval of 60 to 120 such that f prime of C is equal to 0? So basically your idea here is that, sorry, let me zoom in and see if I can get this a little cleaner for you guys. Must there be exist a value of C such that f prime of C is equal to 0? So your idea here is that there must be some value of C, because the idea is what we're trying to do is f prime of C is equal to 0. That's what we had here. I wonder how we justify our answer. I guess you guys don't need to know this, though. That's the thing. Because there's something called Rolle's theorem, which I don't think is completely right to say this, because if we did f of 60, that's equal to 0.1. So f of 60 is equal to 0.1. And if we did f of 120, oh wow, that's also equal to 0.1. F of 120, that's also equal to 0.1 equal. Since the value has, since it has the same value at both endpoints, there must be some value C. Because these are the same values, this is what I would write down if I were justifying my answer. There has to be some value C where f prime of C is equal to 0. That is basically the idea. And the thing there is called Rolle's theorem. I don't really know how to explain it on stream, though. Let's just go to the next one. I apologize. I may not know the correct AB way to describe that one. The rate of flow of gasoline in gallons per second can be modeled by G of T is equal to T over 500 cosine of... Jesus Christ. Okay. For 0 to 150, using the model, find the average rate of flow of gasoline in the time interval 0 to 150. Show the setup for your calculations. Jesus, this is going to take a second. All right. So the idea is that this is our function that we are given. And so we must, what do we do here? 1 over 500. Oh, no, we have to differentiate this, don't we? Oh, this sucks. Okay, so we have to differentiate this function right here. And that sucks because this is the power rule. All right, yeah, so basically we just have to differentiate this and plug in whatever... What do we need to plug in? Find the average rate of time. Okay, yeah, so we just need to plug in stuff. Give me 1 second. So let's first do the power rule on this one. G prime of 140. Let's do the power rule. This is going to suck. Sorry, I've been procrastinating this. Okay, so let's zoom in. See if I can get this all written down. It's going to take a while. G prime, I'm going to need as much space as I can get. G prime of t is equal to 1 over 500. First term the same. Cosine of, that's the derivative of the first times cosine of, it'd be t. We keep the second one the same. So t over 120. This is the power. This is the product rule in case you're wondering what I'm doing. Plus, we keep the first. No, we do the derivative of the first. Negative sign. That's the derivative of this one. Or the derivative of second. Times t over 120 squared. Times the derivative of the first. So 2t over 120 squared. That's right. Yeah. Derivative of the first, derivative of the second. I think we got that right. Sorry, it's a lot of rules. So then we have to do, we basically just have to plug in this one right here, g prime of 140. Gosh, this is so much. Oh my God, I've been reading the wrong question this whole time, haven't I? Oh my God, I've been reading in this one right here, the D. Yeah, so this D is the one I've been reading. So we just did the product rule for this one right here. This D problem, that is this one I just did. Using this model, find the average rate of change. This one is just an integral. This one would just be an integral. So you would just do the integral of, we'd get 1 over 150 on the outside because it's 150 is the interval, and then we go 0 to 150. Sorry, this is an integral, I promise, of this integral of 0 to 150 of gt, which is this one. So I'm just going to write gt. It's of this function right here. And then I would plug that into my calculator, and you get an answer that's 0.0828. About there, I believe. So this one is for C. This one is for D. So this one now, because we have to plug in G prime of 140, we basically just plug in G prime of 1. We plug in any part of T is going to be 140 in this one. So G prime of 140 for this one above, which we differentiated. And then if you plug that into your calculator, which I'm not going to do, I already have an answer key up on the side here. So that's negative 0.000182. And that's gallons per second because it's double. Thank you guys for sticking with me on this one. So yeah, we did all of FRQ1 here. I'm sorry if that made sense to you. I totally just misread the wrong question. Using the model G, find the value of G prime. So because it's G prime here, we would have to use this one. We would take the derivative of this one. That's what I did here. I took the derivative. I used the product rule because these are two functions multiplying by one another. And then I found the derivative. I plugged in the 140. And then on this one, I just the average rate of change, I did 0 to 150 of the function with the 1 over 150 on the outside, because that's the interval. And yeah, so these would be all our answers to the problems. Let's see if I can circle all of them. Maybe I can circle them in green. Roughly. Remember to write, like, obviously this 0.00182 would be gallons per second. This is f prime of 0 equals 0, or sorry, the 0.1. Oh yeah, sorry, this one was just the justifier answer. You're all good. And the 0.1, this would be 8.3 gallons. So just remember to write what each of these are. Gallons, whatever. This would be gallons per second right here. This one, sorry, gallons per second. Sorry. Did that FRQ make sense to you guys? I want to make sure it did, because that one is a little difficult. Do you guys want to try this one? We can. Before I have to go. When do you use the 1 over b minus a integral, and when do you use the f of b minus f of a? So the 1 minus a integral is the So this guy's asking, when do you use this form, f of a minus f of b over b minus a? Sorry, it should be f of b minus f of a, b minus a. This is the average rate of change. So essentially when you're trying to find the area across all functions, you're going to, not the area, I mean. So remember, the integral is the area under the curve. This is the average rate of change. So between 2 points of a function, what is the average rate of change? So this is to find the slope of the secant line right here, this one right here. Anyway, we are going to, do you guys want to go over this second FRQ here? I can totally do it with you if you'd like. Let me make sure I have all of my notes on the side here just to make sure we don't get sidetracked. I apologize. There's like not any space on these FRQs. You're going to have an extra sheet they give you because the FRQs are on paper. The actual MCQs are going to be online, but you'll have paper obviously to write if you need to do your work. So if you need to, you'll have a bunch of space to do your work. So you'll be fine on the FRQs, just so you guys know. One second, guys. Sorry, I'm just getting this up on my screen. Want to make sure I have everything ready for you guys. Okay. All right, remember, these are graphing calculator FRQs. So, oh, sorry, you guys can't see, can you? These are graphing calculator FRQs. So make sure you have your calculator present and use them if you need to. You don't have to, though. Not at all. Don't worry about it. So anyway, so Steven swims back and forth along a straight path in a 50-meter long pool for 90 seconds. Steven's velocity is modeled by v of t is equal to 2.38 times e to the negative 0.02t times sine of pi over 56t, where t is measured in seconds and v of t is measured in meters per second. Find all times t in the interval at which Steven changes direction. So this one we are actually going to use our calculator because you kind of have to for this one. So you know, I gotta get the calc, short for calculator, on the screen. Put it here. So we had our function from earlier. Let's actually now clear this and put our new function in. So 2.38 times e to the negative. No, this is the Kecht form. No way. 0.02 x also multiplied by sine of alpha y equals pi over 56. Just like that. Oh, and I forgot the x. I plug that in right? Yeah, looks like I did. Okay. So now let's take a look on the graph. T. All right, well that's not that great. I think we need a bigger window, yeah, because it's 0 to 90 here, so we need a bigger window. So we got to go x min is 0, x max we'll put at where's the x max? 90. It's like that. Okay. Well, clearly we could shrink this down, unless it's actually really big and I don't know about it. Okay, no, it isn't. So we can clearly shrink this one down. So we can put the y max at like, I don't know, 2 maybe. Is 2 too short? Actually, 2 is kind of perfect. Y max at 2 and the y min at, let's say, -2. Just like that. There we go. That gives us a better thing what we're looking at. Okay, so for all times t in the interval at which Steven changes, find all times of t in the interval at which Steven changes direction. Sorry, I know you can't see that. Give your reason for your answer. So all times t. Give me 1 second here. I want to make sure I get this right for you. So we have our velocity equation. We just need to make sure we get it at any time Steven changes direction in the velocity equation. And anytime Steven changes direction is going to be actually where it changes from positive to negative. Now, where does it change from positive to negative? You see it is at this point right here. It does it at 1 point. So find all times. It is just 1 point that Steven actually changes direction. So to find that point, I go second calc, or trace, sorry. And we go to 0 because we want to find the 0 on the graph. So it asks us to go to the left side of it, so we can push enter. We can ask us to go to the right side of it, so we can push enter, and then it asks us to guess. So we just relatively go into where that point is, and we say guess. And then it says it at y equals 64. So would that be it? Y equals 64 as our answer. Y equals 64, I believe, is our answer, but sorry, it's saying something different here as the answer. I mean, interesting. Did I plug it into my calculator wrong? Sorry, I don't know what's going on. I think I might have plugged it into my calculator wrong. 2.38 e to the negative 0.02k sine of pi over. Did I do pi? Oh my god, I did e over 56. That's hilarious. Oh my god. Okay, we need to do pi over 56. Sorry for anybody who caught that. I didn't realize that we didn't do pi over 56. Oh my god. All right, where is pi on my calculator? My god, it's been so long. Where is pi? I'm such a noob. Where is pi on my calculator? Why is this so hard? Where is pi? I gotta find pi on my calculator. This is so hard. I'm such a noob. Where is it? Pi. Where are you? Oh, it's right there. Okay. I was looking for it. So instead of e, it is going to be pi. Okay, let's look at the graph now. Actually, the graph looks relatively the same. So we're gonna go second, calc. Find our 0 again. So we go from the left side, we go to the right side, and we go to the middle. There we go. X equals 56. That's our answer. And we'll just write it down. X equals 56. I know you can't see. Oh my gosh. X equals 56. That's our answer because that's the point we're finding. There we go. Okay, find Stephen's acceleration at time t equals 60 seconds. Show the setup for your calculations and indicate units of measure. Is Stephen speeding up or slowing down? Give a reason for your answer. All right, I don't believe we need the calculator for this one. We might need it for a little bit later, but we'll see. So we need to find, this is v of t up here. So we need to find v prime of t, which is a lot. So the idea here is that a of t is going to be equal to v prime of t, which is going, so we can plug stuff in. So we get a of 60, which is the one they're asking us for. A of 60 is equal to v prime of 60. And if you plug this in on your calculator, I think you guys already know how to do this. I won't bore you with it, but if you plug this in on your calculator, you get negative 0.036 meters per second squared. At t equals 60, this would mean we would have to solve for again on our calculator, and at t equals 60, we plug this in, we would get negative 0.160 as our answer. And because velocity and acceleration are both negative, because this is velocity here, sorry, is negative, acceleration is negative, because they are both negative, this means that it would, v of 60 is equal to there. So because these are both negative, it means it is speeding up. That is just the idea here. Sorry, I know I skipped over a lot of the calculator stuff, but I'm assuming you already know how to do stuff on a calculator, or you could use Desmos as well and go along the graph, but yeah. All right, so find Stephen's distance from the position of time at t equals 0 seconds to its position at the time t equals 80 seconds. So this is more talking about displacement. Show the setup for your calculations. So your idea here is it's going to be the absolute value from the lowest number, which was 20, the highest number, which was 80, of the function that we had earlier up here. So v of t, I'm not going to write down the whole thing, but it's just this function v of t up here. And then, actually that's all it is. So essentially we just plug that into our calculator. Sure, why don't we do it? I'll show you guys. I skipped over the calculator on the last one, so I'll show you how to do it on this one. Oh my gosh. Sorry, I'm such a live streamer here. Oh my goodness. There we go. So we will plug this in. So we go to math. Or math 9, remember, is the integral. We go 20 to 80 of our function, which, what was our function again? It was, cannot see it, the 2.38 e. You also could have stored this earlier. Probably would have been easier to store it. I'm going to be real with you. Second, or to the raise to the power of 0.02 x times sine of pi over, say, alpha y equals pi. Where was pi again? It was here, right? Pi over 56t, 6 or x, I guess, with respect to x. So we solve that one on our calculator, and we get 23.389. This is equal to 23.38. Or sorry, not 9. It would be 384. Let's go check my answer really quickly. 3.384. That is right. And this would be, of course, meters. All right, last one. Find the total distance Steven swims over the time interval 0 to 90 seconds. Show the setup for your calculations. So the total here, we are given a few things because we already know the integral from. Well, let's see here. What can we do? Because the idea is that we're just trying to find the integral from 0 to 90 of the absolute value of v of t, which we had up here earlier. But why don't we actually model this by a function instead and say it is, because we already went up to 56 earlier, so we can go up to, and we went up to 90, or we can go 56 to 90. So we model this with two separate integrals. So we go 0 to 56. This is how you do it with the absolute value, by the way, of dt minus the integral of 56 to 90. This is the total time with the absolute value dt. And then again, I'm not going to bore you with this whole thing. You can plug this one into your calculator. Of course, v of t is your function up here. Again, I kind of forgot to store it, so I don't want to write that all out. But if you plug this into your calculator, your answer, you should get 6.164. Sorry, this should be 62. 62. Oh my gosh, this is so rough. I'll just rewrite it. 62.164 meters. There we go. That's FRQ2. So it's just some stuff with integrals, area, and change. So yeah, we did these two for you. If you need more help with FRQs, just I think there's great videos online about them. But yeah, I'm sorry if those were a little bit confusing. I had very limited space to work with, and I didn't want to use my calculator every time. But those are your ideas for these FRQs. Thank you guys for that. He forgets the absolute values. No, I don't, because when I put the integral in, the way that I rearranged it makes it so the absolute values are mute. I don't need to put them. No, he was putting, yeah, positive and negative separately. Yep, you got it. No worries. Okay, guys. It is 6:03. We've been doing this stream for over 3 hours now. My goodness, this has been a fun stream. Everybody, I want to say thank you so much for tuning in today. I actually planned to have more, but I guess we just went through this stuff so fast. So if you want to do this practice exam, the one that we just went over, all these questions, you are totally free to. It's no big deal at all. I'm totally happy with you guys doing that. I'll keep it in the description of this video. This live stream will be available after we finish. The live stream will be available, so don't you worry. And then if you're wondering the question's answers, here, I'll scroll through them all right now so you can see the answers for each question. And then you can check your work later in the stream with all my work that I did as we went along. Just scrolling along here. You can see all the answers we had. But yeah, thank you guys so much for tuning in to today's stream. I really appreciate it. Let me take a look at this Be Right Back screen that I never got to use. Yeah, so that's my screen I didn't get to use. It was really cool, too. It took me a while to make. So everybody, just know, if you need help with anything from units 1 to 6, I have videos on this channel. They are in my AP Pre-Calculus, or not Pre-Calculus, AP Calculus. If I go under, sorry, 1 second. Give me just 1 second. Yeah, if we're on my YouTube channel, as you can clearly see, we have our live stream up here. But if you go under my playlist, you will see I cover lots of courses on this channel. But the big one I cover is actually this one right here, which is the one you guys want to know, which is Calculus AB and BC. So I have units 1, 2, 3, 4, 5, 6 here. I was unfortunately unable to get to unit 7 and 10. I apologize for that this year. I'll try and do it next year. But yeah, so I have good units. These are great videos. I recommend them. If you need help with unit 7 and 8, you can, one channel I really do recommend is the Algebros. These guys have helped me to get through all of my calculus this year. They've been great help. I do really cannot recommend these guys enough. And also, I just want to really quickly point out, some of you guys wonder why I wasn't able to finish my AP Calculus videos this year. Like, why exactly was I not able to finish? Well, let me give you a quick overview of what an AP Calculus video looks like to edit. I'm not going to show you my editing process or anything. I'm just going to show you what the project looked like in total. So, for example, give me 1 second here. So if you're wondering what exactly my what an editing project for AP Psychology looks like, this is it. This is my AP Calculus Unit 6 video. So I'm sure you can imagine every single part of this just took forever to make. Every single part of this. Imagine how much you have to go through here. So when you make a video, when I make a video, you don't know this, but probably about every minute I spend editing a video is about 2 hours of editing time. Or sorry, every minute the video is up. So like this is a 20-minute video. So every minute it is about 2 hours of editing. So for 20 minutes, this video probably took 40 hours to edit. So these videos take so long, which is why I was unfortunately not able to finish your course this year. So I once again apologize, guys. But yeah. If you're asking what units are mostly covered on the exam, I got you. Really quickly, I will show you. Because I actually was prepared for somebody to ask that question today. So the units, here is your exam weighting, guys. This is your exam weighting. So if you're wondering what units are covered more, well, here you go. Units 1 and 2, you don't have to worry about the BC because I'm assuming all of you are in AB. 10 to 12%. 10 to 12% for Unit 2 as well. 9 to 13% for Unit 3. 10 to 15% for Unit 4. Then we go up. Unit 5, this is the one where you have the you're relating functions and their derivatives. This is a little bit more. And then the big one, Unit 6, integration and accumulation of change, because it's all taught in this unit. And then Unit 7 is not that big. This is separation of variables, stuff like that, because it's not that difficult. All you really have to do is know is how to do separation of variables. And then Unit 8, which is like the cross sections and the rate of change or accumulation of change area between two graphs. This stuff is not too difficult either, but it's also not worth a lot on your exam. Like these, like this one is not worth a lot. This one will be worth a little bit, but again, it's not too difficult. Just memorize your formulas. But yeah, everybody, that is going to be it for this stream. Thank you, everybody. I know I got a lot of jokes in the chat. People are saying, I'm going to fail, I'm going to fail. No, you aren't, all right? Listen, to get a 5 on the AP Calculus exam, I believe all you have to get is 64% of the questions right, which is a D. If you've been scoring better, if you're in an AP Calculus class and you've been scoring better than a D on your tests, then you are going to get a 5. You are going to get a 5. If you've been scoring better than a D, then by that logic, you are going to get a 5. Just know how to do your questions. Just know how to do them. I cannot say this enough. You guys are capable of this. For those who were with me last year for pre-calculus, that test was so easy, wasn't it? It was so much easier than you thought it would be. This test is going to be the same way, all right? Like, once again, thank you guys so much. Thank you guys so much. Yeah, this is me signing off. I appreciate you guys once again. Get a 5 on that exam. I will release a YouTube short tomorrow morning. Wishing you all luck on the exam. But yeah, you guys are chilling. You guys are so chilling. I believe in you. But yeah, thank you once again. And yeah, what should I even say? I don't know what to say. How do I say bye? So rough.